Who do you think I am?
And
a Gusto. And Jan.
But since I was in a good company, I accepted this. And I will discuss today theory on collective nuclei at the shape phase transition point and beyond. And I want to give also quite a number of experimental data to compare the theories to. So you will see today more data than you have seen before, probably for two reasons, because I think some of you are also experimentalists and you want to see how the theory that you study here really works in nature. And secondly, I also think that the theoreticians among you should know how to obtain the data that you do your theory on. So I was helped by putting together this presentation by Dr. Bella and Dr. Krugman, two postdocs of mine, and Dr. Krugman is also with us, and he will also help you and me when we do the exercises in the afternoon. So here's an outline of my presentation. I will remind you briefly at what you have studied already during this week, or during these days here, on the rigid rotor, nuclear deformation a little bit. Then I motivate the phenomenon of the shape phase transition and discuss the X5 solution, that is an analytic solution to the geometrical model close to or at the point in the nuclear charts where vibrational nuclei turn into deformed nuclei as a function of increasing particle number. Then I will discuss at more length variant of this or generalization of this analytic solution, which is also analytic, but more this confined better soft rotor model. And the main physics in these models is the physics of evolution of deformation in a soft potential, which causes this phenomenon of centrifugal stretching. And I will show you evidences for this phenomenon from spectroscopic data, from level energies, and also from decay transition rates, electromagnetic transition rates, which means lifetime data on some nuclei. And then I will discuss some, if I have time, some electric monopole transitions, and then conclude. So when you do nuclear structure studies, you do some spectroscopy on nuclei with high resolution. You can do gamma ray spectroscopy, let's say with germanium detectors. And then you see typically in a nuclear reaction these sort of gamma ray spectra. You can recognize several gamma ray transitions here. Some are very prominent. And you see also regular features. Here I have labeled a few gamma rays. I mean, there is an even nucleus, Irby 160, is deformed, and you have gamma ray transitions from the 2 plus to the ground state, 0 plus, 4 to 2, 6 to 4, 8 to 6, 10 to 8. So this is like a band of transitions that are also in coincidence. So they belong to the same structure. And you can study angular distributions, you can study coincidence relations, and then come up with a level scheme, a scheme of excited states and gamma ray transitions that connect them. And here again, this example from this nucleus here, Irby 160, has an even nucleus. It clearly has a 0 plus ground state, and then there are states on top of this. 2 plus 4 plus 6 plus 8 plus, so the ground state band. And then there are side bands also, I mean, that come from gamma ray transitions in between here with weaker intensity. There's a band that starts with the 2 plus and has also the odd spin numbers 2, 3, 4, 5, 6, and so on. This is the so-called gamma band. And then there is a band that is based on a 0 plus. This is here dashed because it wasn't seen in that experiment, but it was known before. So 0, 2, 4, 6 looks like the ground band, the k equals 0 band, and there are decays into the ground band, and also in this band. And you want to make sense of this level scheme, and one important number that characterizes these deformed nuclei that you have learned already from Professor Kasten is this ratio of excitation energies from the first 4 plus to the first 2 plus, this R4-2 ratio, which in this case here is 3.1. Why do I say this? Because there is this rigid rotor paradigm, which I will discuss in a minute. Here's another example of such a ground state band, dysprosium 164, where this R4-2 ratio is larger. So these R4-2 ratios can vary between different nuclei. And here are the level energies. So in this case, 242 kV divided by 73.4, that is 3.30. Not exactly 3.33. Why do I say 3.33? Because one very easy theory you can compare this to is the rigid rotor theory, where you just have angular momentum, the L square operator, and that produces eigenenergies that are proportional to LL plus 1 or II plus 1. And if you would normalize, so you have this h bar square over 2 theta, the moment of inertia in front, and if you normalize this number to the experimentally observed level energy 73.4 kV in this dysprosium 164, then this II plus 1 rule would then predict these energies here. So when it was adjusted to the data at this point, I mean, you see that it fits quite well, 244.7 instead of 242. But then you start to notice also there are some deviations. I mean, here you are 5% off, and here you are 10% off. So the nuclei look like rigid rotors, but they are not exactly rigid rotors. There are differences. As I said before, so the rotational energy of the rigid rotor is II plus 1 times the constant. And rigid rotor means this moment of inertia does not change along the band. It's just rigid. It doesn't matter how fast you spin the nucleus. Its moment of inertia stays constant, is independent of the angular momentum. And in that case, so if that holds, then you have a ratio of the first 4 plus, where you have here 4 times 5, divided by the first 2 plus, where you have here 2 times 3, that is exactly 3.33. And this constant in front drops out because this constant was identical for all the same levels. And you have seen this dysprosium 164, quite a good rotor, deviated a little bit from this prediction. Another example here, uranium 236, also a strongly deformed nucleus. There are deviations. I have plotted here. Its first 2 plus has a different energy, of course. It is at 45.2 keV. But I have adjusted the scale such that the 2 plus bars here, they are all at the same height. And then the 4 plus, you see then the energy here, you can compare the bars. They start to deviate from the rigid rotor in the same way as this dysprosium 164 has deviated. And it happens that also the R4-2 ratio here are identical between dysprosium 164 and uranium 236. Very close, 1% within the rigid rotor limit, but when you arrive at the 10 plus or 12 plus, the deviations are already 10-15% from the rigid rotor formula. So there must be something in addition to this rigid rotation. You have studied already the Bohr Hamiltonian. Here, Professor Caprio has discussed this topic a lot. So I just put it up because I mean we are discussing the behavior of these spinning nuclei in terms of the Bohr Hamiltonian, where we consider the shape of the nucleus, this quadrupole deformed shape, and its orientation, and you can then go to the intrinsic frame, which means you go to a coordinate system that is fixed to the deformation axis of the nucleus, and then you have two parameters, two dynamic variables, that is the quadrupole deformation parameter beta and this triaxiality parameter gamma. So you have a kinetic energy term here, you have a centrifugal term there, and a potential in terms of these deformation variables beta and gamma. So this is a centrifugal term. I mean, that is traditionally written Q here, but you can also write angular momentum L squared in the different directions. And you see the moment of inertia, I mean, that is typically L squared over theta, so the moment of inertia and this Bohr Hamiltonian, that is proportional to beta squared. So if you compare this to the rigid rotor constraint, which was theta must be constant for all angular momenta, then you see that the Bohr Hamiltonian can be consistent only with the rigid rotor if you fix beta for every state independently of the angular momentum by the potential, and this you can do exactly only if the potential would be a delta function in beta at a certain beta 0. Right? If you would have a potential as a function of beta, which would be infinite everywhere and only at a certain beta 0, you would allow to have finite values. Well, you don't have to switch on to that. Where you have finite values of beta, and that would keep beta for all the states with angular momentum at that rigid value beta 0. Okay, thank you very much. Of course, a potential as a delta function, that is quite unphysical. Another nucleus, another data set, Samari 152, which has historically played a very important role. There is this ground band, the R42 ratio is 3.01, but as before, also in other nuclei, there are other bands, like here's another k equals 0 band, with 0 plus, 2 plus, 4 plus, and other states. And here this band has an R42 ratio by itself. It is 2.69, and the 0 plus state is close in excitation energy to the 6 plus here, and has an excitation energy relative to the first 2 plus of 5.62. So it's 5.62 times higher in energy than the first 2 plus state. Nuclear deformation, so we have seen nuclei with different alpha-2 values. Nuclear deformations evolve over the nuclear chart. And here is a plot of where you can find in the nuclear chart, so proton number, neutron number, the different deformations. I mean, this is the area of the rare earth nuclei with strong quadrupole deformations. Here are the actinides with strong quadrupole deformations. I have shown you examples from these regions. And then you see the magic numbers where you have small deformations, vibrational nuclei, and then you have regions where these deformations change quite rapidly as a function of particle number. This is the ratio, the alpha-2 ratios in such a region of rapidly changing deformation. So you have values from 2, which I think you have seen this graph already from Professor Kasten, in the samarium isotopes going from 146 samarium to 160 samarium. So these values go from nearly 2 close to 3.33. And in terms of this potential, as a function of beta, you go from a parabola, a harmonic oscillator, so beta square, to something which is close to a delta function. I mean, that is not really a delta function, but there's a strong minimum at a certain finite value of beta. And if you want to go smoothly from here to there, I mean, you must somehow lower the potential at a finite value of beta, and then you must encounter a situation where the low value at beta equals 0 and this low value of the potential at a finite beta, they are almost equal. Right? So you must encounter in this evolution a situation where you have a sort of a flat bottom here and then a steep rise at the side. And this is a situation which was discussed later in the last 15 years or so as a critical point of a shape phase transition, a shape transition which goes from spherical vibrational to more or less rigidly deformed. There is an analytic solution to such a transition, an theoretical solution to the Bohr Hamiltonian, which is called the X5 solution, which I will discuss from now on in much more detail. And here are the parameter-free predictions of this analytic solution. There are a few characteristics. There is an R42 ratio, and this analytic solution, which I will discuss in the next slide, gives a number of 2.90. So for the energy of the first 4 pluses to the energy of the first 2 pluses, 2.90. And in the excited k equals 0 band, this ratio is 2.80. And there's an analytic and a parameter-free prediction of this model is also that there occurs a 0 plus state close to the 6 plus state in the ground band with a relative excitation energy to the first 2 plus of 5.65. And here's again the samarium data that I have shown you before, where this R42 ratio deviates from the rigid rho in the ground band, 3.0, much closer to the 2.9 to the parameter-free prediction of this model. The R42 ratio in the excited k equals 0 band is lower than that in the ground band, as here in this model. And the excitation energy of the excited 0 plus is close to the 6 plus of the ground band, and the relative excitation energy to the first 2 plus is 5.6, like here. So there is some evidence that this solution, which I will discuss now, really has occurs in nature. And these data, by the way, they were found by Professor Kasten.
And others.
And others. Okay, so what is now this X5 theory that I hope that you want to learn now and you want to study? That was found and developed by Professor Iacchello at Yale University, as I said, about 50 years ago. So that is what I said in words already, a wave function of the geometrical model in the laboratory system that depends on 5 variables, 3 angles, the Euler angles of the orientation of the deformed nucleus, and 2 intrinsic variables of the quadrupole deformation in the intrinsic frame, this beta and gamma. And that is written here already in a way where one assumes that the beta deformation and the gamma deformation are separable. Professor Caprio has discussed this. So the Euler angles you can parameterize, or write as in terms of these D functions. So we only have to deal with the intrinsic variables here, and we assume that beta and gamma is separable, and gamma can be treated in this case here in the X5 solution, let's say, as a harmonic oscillator. We will not deal with gamma. The thing we focus on is the beta. And then the Bohr Hamiltonian transforms into this radial equation as written here. So there is a constant with a mass parameter in front, h bar square over 2b. And then there's this kinetic term, 1 over beta to the fourth, d over the beta, beta to the fourth, d over the beta. And then comes the centrifugal term, minus 1 over 3 beta square, LL plus 1. So this is the L square operator. Plus the potential in terms of beta. And then, it's an eigenequation, of course. So there's a wave function, which we call psi. Psi sub L with an index L, that is the index for the angular momentum state you are looking at, 0 plus 2 plus or 4 plus, is equal to the eigenenergy times the eigenfunction, so the eigenequation. And at the critical point, we said that we encountered a situation where the minimum of the potential at beta equals 0 and at a large value of beta are equal. And then there is a steep rise. And the simplest way to model this, and which also gives then an analytic solution, is to use an infinite square wave potential. So you have a low value at beta equals 0, a flat bottom, a low value at a finite large beta, and then a steep rise. Right? And the simplest way you can do it, you have a flat bottom and then infinite high wall. Which means, so everywhere where the potential is infinite, that means that the quantum mechanical wave function cannot live there. It can tunnel into forbidden parts of the parameter space, but not to regions where the potential is infinite. There the wave function must be exactly 0. That means there are at least boundary conditions for the wave function. The wave function can live only in this part of beta. They can contain values of beta that range from beta equals 0 to some finite large value of beta, but they cannot contain pieces with other values of beta, and wave functions must be continuous. If they are 0 in the parts where the potential is infinite, then the wave functions must have nodes at the boundaries. They must go to 0 because they must be continuous, and when they are 0 outside, there must be 0 at the borders. So there are boundary conditions. And these boundary conditions are written here. So the wave function psi for every angular momentum state L must be 0 at this beta wall. Beta W means where the wall starts. Right? And of course at 0 there must also be 0. So then you have this quite complicated differential equation with that boundary condition, and you want to solve it. And the miracle is, and you will prove it in this afternoon in the exercises, that this is not a miracle but just mathematics. If you now change variables, instead of using these eigenfunctions psi, you use new functions psi tilde that are simply the old psi's multiplied by the deformation variable to the power of 3/2. And you change the variable beta itself to a new variable z, or z, which is a square root of parameters that appear here, the eigenenergy and this constant here in front, times beta, then this equation transforms into the Bessel equation. The Bessel equation has been studied, I think, in the 19th century, but I'm not absolutely sure, by mathematicians. For some other reasons, it is an interesting differential equation. And the solutions to the Bessel equation are the Bessel functions, and they are tabulated in mathematical textbooks. So this differential equation is complicated but solved. The solutions are known, and they are tabulated. You cannot solve it in closed analytic form, but these Bessel functions you can find, and you can plot. And in Mathematica, for instance, you can have tools for just showing the Bessel functions, and then you can look at it. I will show you.
Excuse me. So
Yes.
what is the meaning of V beta? just for
Of beta W, what is the meaning of
V,
the
V,
V
potential.
of beta? That is a potential.
just
That is-
to define boundary condition.
Well,
does
we said before, when you have a harmonic oscillator, you have V of beta is proportional to beta squared. Right? When you have a rigid rotor, V of beta is like a delta function in terms of beta, minus delta beta minus beta 0. That is a rigid rotor. And now we wanted to have a potential for beta at the shape phase transition point, where you have a low value at beta equals 0, a low value at a finite beta, and then a steep rise. Then we take this potential. So V of beta is our square well. So the white part is the allowed stuff. So here the wave function can live, but this here is infinite. Okay, so then let me write it up. V of beta is equal to 0 for beta between 0 and some finite value, which I call beta W, and is infinite otherwise. Beta larger beta W. Okay?
Okay, so this model is for just for the
It's
transition.
It's at the critical point.
Yes.
Exactly. So it's just for this, and it's not flexible. Right? You cannot change it in this mode. So you have one potential, and you can solve it. Are there other questions? You can. When something's unclear, please ask me. Okay. So now we do this transformation of variables of beta into z, which is a constant times beta, and this wave function psi as into psi tilde, and then we get the Bessel function, the Bessel equation. The Bessel equation is the second derivative of your function, so y2 prime, or psi tilde 2 prime, plus the first derivative divided by the variable, plus 1 minus a constant in square divided by the variable in square, times the function itself is 0. That is the Bessel equation. And the solution to the Bessel differential equation are the Bessel functions. And the Bessel functions, they have an index here, and that is just this number, this constant that appears in this Bessel function. And in our case, this constant here is, you do this, you verify this in the afternoon in the exercises, square root of the parameter that appears here, LL plus 1 divided by 3 plus 9 fourths. So I cannot tell, it just turns out from this transformation of variables. What are now the Bessel functions? Here are the Bessel functions. In one example, in the simplest case, or in one case, for the ground state, L is 0. So when you have angular momentum 0, then of course the K quantum number must be 0. Why is that so?
Projection.
What? Yes?
Projection of the symmetry axis. So
Exactly, it's a projection on the symmetry axis, so when you project a 0 vector, then the projection is 0. So K quantum number is 0, so this is 0. L is 0, so this is 0 here. So for the L equals 0 state, then this square root reduces to square root of 9 over 4, which is very convenient. 9 over 4 you can solve in your mind, so it's 3/2, so 1.5. Right? So this is the Bessel function, J 1.5 of the variable z, right? Or of x or whatever you write here. So this is the z-axis here, and this is the Bessel function J 1.5. There is a second type of Bessel function, the Bessel functions of second kind. So this is the y function. The j functions are the Bessel functions of first kind. The difference is the Bessel functions of first kind start at 0 for the variable being 0, and the Bessel function of second kind, they start at minus infinity at the variable at z equals 0. And then they are oscillatory, and they oscillate with the same frequency. But you remember that we had these boundary conditions, the wave functions must be 0 at the variable being 0. That means the solution can only be the Bessel function of the first kind, because that is the function which starts at 0 for the variable being 0. Right? So there cannot be a contribution of the Bessel function of second kind, which is, both are solutions of the Bessel equation. Right? But the wave functions we are looking for only contain these Bessel functions of first kind. Okay, so we now know that the solutions of this Bessel equation here are these Bessel functions with this index, which changes from level to level, because L changes. So the angular momentum is 0, 2, 4, and then does this index change, and also these Bessel functions change slightly. Yes?
So just the definition of nu changed from slide to slide? This one has no
That
K.
is correct. The definition of this nu changes from state to state, because the angular momentum L changes from state to state. You see here in the Bohr Hamiltonian, there is this LL plus 1.
I think he meant in the next slide there's a minus k squared in the definition,
Well,
No. previous slide.
Ah, okay. This is a generalization to the cases where you can have k not equal 0. So what I have written here is, I was interested, I have written it up for k equals 0 bands. But if you have also k not being 0, we only deal today with k equals 0 bands, so don't worry. But the other equation here, that was more general. If you also consider gamma bands with k equal 2 or k equal 4 bands, then you must modify this. It's then more general. You can also, at one point I will also discuss a gamma band, and then I have used this index. So this is more general, and in case of k equals 0, that reduces to the other formula that I have shown. Okay, so we have the solution, but we haven't dealt yet with the boundary equation, with the boundary conditions. So our boundary condition was that the wave function must vanish at 0. This we have dealt with already by having the Bessel function of first kind only. But we also have the condition that the wave function must be 0 at the wall. Okay? So we can use only those solutions that produce a 0 for the parameter z being the value at the wall. So where you plug in here was the definition of z. So there's here this constant, which came with the Bohr Hamiltonian, and there's the eigenenergy, which we still don't know though, times beta. But when we plug in here the beta, the position of the infinite wall, then and we put it into the Bessel function, then this must be 0, because that is our boundary condition. Okay, but the Bessel function has zeros. Here's a 0, first 0, there's a second 0, and so on and so forth. So that means that this number here, this ZW, so when we plug in here this beta at the wall, this must be a 0 of the Bessel function with that index. And that means that we have, for a given potential with the width beta W, and parameters of the Bohr Hamiltonian, this mass parameter, we know we can read off this 0 of the Bessel equation with that particular index, and then we can calculate the eigenenergy for every level as a function of the angular momentum L, and as a function of which 0 of the Bessel function we take. Right? So we know that this ZW or ZSL, you can classify them as in terms of the nodes of the Bessel function and the angular momentum is equal to this constant here times beta w. You can solve for the eigenenergies, which we do here. So you square it and then you solve for this. So then you have a constant for the energy of the S state with angular momentum L is a constant times the square of the zeros of a Bessel function with a certain index. Yes? And now we have produced solutions for a spectrum, which I will plot in a minute.
So here you're looking for the zeros of the Bessel function, so you can get the energy eigenstate.
That's correct. So from
Yeah.
the boundary condition, we get the eigenstate.
Why did you show us the second type of Bessel function?
Please wait a few minutes. I will need it later.
Okay.
Okay. Another question?
So the first time the zeros are the first type of determinant energy.
Yes. I will discuss it now. I will show you now. So, you want the excitation energy of the S state. Take the S as the first, okay? Then it's the ground band. You want the energy of the first state with angular momentum L. Take L equal 0. Then you have the ground state. So that's the first 0 plus state. Then, so if you have the first state with angular momentum L, then you have as an excitation energy, that is the absolute energy of that state minus the ground state, of course. The ground state is the first state with angular momentum L equals 0. So S is 1, L is 0. And that means you have this constant in front times the square of the first 0 of the Bessel function with angular momentum L. Remember, this index nu was a function of L minus the square of the first 0 of the Bessel function with angular momentum 0. Okay, so now you have the excitation energy. You can calculate, let's say, the excitation energy of the first 2 plus state. Okay? Then, for the first 2 plus state, that is the first, so S is 1, the first 0 of the Bessel function. Angular momentum L, that means in this nu of L, there appears now 2 times 2 plus 1. Minus the ground state energy, then you have the excitation energy of the first 2 plus, which is just this constant times the square of the first 0 of the Bessel function where you have used the angular momentum L minus the square of the first 0 of the Bessel function where you have used the angular momentum L equals 0. These numbers you can read off a mathematical textbook, or you use Mathematica, and this is just a constant from this volume term. Or, even simpler, you want to get rid of this constant, so you take ratios. Then, I mean, there's the same constant here for the excitation energy of the first 2 plus, then here for the excitation energy of the SL plus. You just divide them, so then this constant drops out, and all energy ratios are just determined by squares of zeros of Bessel functions. So you cannot change them anymore. Right? So it's there. You have no flexibility. It's just an analytic solution, which happens to be this one. So when you do this, and you will do this in the afternoon, I will give you a table with zeros of Bessel functions. And you just compute these sort of ratios of differences of squares of Bessel functions. And that gives you relative excitation energies. So when you plug them, when you read off the mathematical textbook these zeros of the Bessel functions and you do this ratio here, then you find you have the 2 plus at some energy, so that would be at relative energy 1, and then the 4 plus, you plug in here a different 0 of the Bessel function, then you find this ratio is 2.90. When you put the 6 plus, you get something else, close to 5.5. You can, instead of using the first node of the Bessel function, let me go back to the Bessel function again. Here. So instead, so we are on this Bessel function here, Bessel function of first kind. Instead of reading off the first node of the Bessel function, you can also use the second node of the Bessel function, which has a higher value. So that produces a higher excited state, also with the same angular momentum, which is this one. So there's another 0 plus, and this one was the first 0 plus. That is another 0 plus, and then there will be higher 0 pluses, right? Corresponding to the third 0 of the Bessel function, to the fourth 0 of the Bessel function, and so on and so on. These Bessel functions are oscillatory, so you have an infinite amount of 0 pluses that have higher and higher and higher excitation energies, and more nodes. Okay? Okay, so, and that is how it compared to data. So this is the parameter-free solution of the Bohr Hamiltonian with this particular potential now. Right? You have previously studied, a rigid rotor or a vibrator. Now you have this funny potential and infinite square well. Solutions of the infinite square well problems are always Bessel functions. And you have, for this potential, you have this solution which is parameter-free and fixed. And you can compare it to data. And there are also these arrows. They are E2 transitions, which I will discuss later, and they also compare more or less favorable from between data and this model.
Sorry,
Yes.
what is meaning of parameter free?
The meaning of parameter free is that in the Hamiltonian, a square well potential has no scale because infinite is scaleless. Right? There is no meaning into having the potential twice as large because 2 times infinity is also infinity. And then all the other parameters that appear in the Hamiltonian here, so the potential doesn't have a parameter, besides this width of the potential. And here's another parameter, this B. This doesn't play a role for the relative excitation energies because these parameters of the problem drop out when you take ratios. In these relative excitation energies, there's no parameter of the Bohr Hamiltonian anymore. Right? So it's completely independent. You can change the parameters. These relative excitation energies are still the same. So you make the width of the potential twice as large. You make the mass parameter 100 times as large. Then the relative excitation energies are still the same, exactly the same. So it's independent of the parameters that you have put into the equation. The relative excitation energies stay the same. Only the scale here, that changes when you change the parameters. So in that sense, relative excitation energies and also relative E2s are parameter free. And here are relative things, so these numbers are parameter free. Yeah?
Something which has always disturbed me, in fact, even wrote an article on it, is that, okay, you take these relative energies, but if you would take now the relative energy of the second 2 plus to the second 0 plus over the first 2 plus over the first 0 plus, you don't have agreement.
That's correct.
Because the moment of inertia is
That
the
is
same
correct.
in both
Yes,
lines.
yes.
Experimenting.
Yes. I think that the moment of inertia, there's a problem in the geometrical model.
Yeah.
I agree. Because, in my opinion, when you do an intrinsic excitation, you do something to the
road.
superfluid stuff, right? So you increase the moment of inertia. So you break pairing and so on, or you reduce the pairing.
But it has never been.
But this is outside of the geometrical model. You cannot describe it. I mean, you know that. I mean, the English formula, you have to go to the underlying particle. Yeah.
So in this X5 model, so you have these infinite square wells. And when you have different energy, different L values, you have different. In order to solve the equation, you take different zeros at the.
of the Bessel function.
Bessel functions.
You take first, you take, for different L's, you take different Bessel
Yeah,
functions.
yeah.
They have a different index.
So if you take the mean value of the beta
Okay.
parameter
Mhm.
with different solutions, the mean value would be slightly going.
I will
higher
show you
value.
this. I will show you this. Just wait. Yes, you are completely right. This will come. I mean, please be a little bit patient.
So, sorry, excuse me. So,
Okay.
why, so the agreement is good?
Why the agreement is good?
Yeah, because
Because we believe that Samari 152 is lying close to this here. This value, 3.01, that is the value for Samari 152. And we believe that the shape phase transition point is somewhere here, probably a little bit before Samari 152. So for these nuclei here, only here, the potential looks somehow close to this flat thing and then a steep rise. Not exactly, of course, therefore it wasn't exact. Right? But that is closest to that point. And I mean, we turn it around. We have a solution for a situation with that potential, and we find Samari 152 being quite close to this prediction. So that means, do you have a question on this topic, Rick?
No, I have a comment after
Okay,
you're done.
that's what I was afraid of. Okay, so Rick.
No, finish what you were saying.
Okay, so we conclude that 152 samarium is lying close to this shape phase transition point.
Remember what I said in one of my first lectures, that these collective models cannot tell you why a nucleus does what it does. It can tell you what it does. And so we find that the nucleus does something roughly similar to this potential. To find out why, you have to do a microscopic calculation. And there have been microscopic calculations by Dario Bretinar and his group. And they show that the potentials are pretty flat.
so if potential is not flat, having two minimum agreement.
He may discuss, are you going to discuss the bump?
Yes, well,
Yeah,
here's
okay.
Bretinas.
Yeah.
Okay, but just wait. So there are other nuclei that agree quite well with this prediction. Neodymium 150, which is an isotone to Samar 152, has an R42 ratio of 2.93, which is within a percent equal to this X5 prediction. And the excited 0 plus state here is also very close to the situation where it is predicted. But the moment of inertia is different, and then there are higher excited bands also. And also the B2 values are sort of close from the trend to the prediction. There are some disagreements. Quite good. So we have seen nuclei that have different alpha-2 values, and some of them have an alpha-2 value close to 2.9, which is the prediction of X5. And then also the location of the excited 0 plus that is predicted. So you can correlate these two observables and compare data and theory. So X5 makes a prediction for R42, makes a prediction for R02. So in this figure, it is a dot somewhere, right? And this dot lies here. And these squares, diamonds, are data from nuclei in that region that we have looked at. This beginning of the rare earth nuclei. And you see nuclei with varying alpha-2 values and also with varying excitation energies of the 0 plus state, but they show a smooth systematics, right? So, of course, this parameter-free model can only produce one dot here, and it lies in the band of the data, which is good already, so it shows that it is relevant. But of course, you cannot describe all these nuclei because you cannot change this model. It just makes one prediction. Now we do different. Why? Because, here is the potentials that were calculated microscopically for some neodymium isotopes. Neodymium 150 is here this thick black line. Here's beta equals 0. This is a quadruple parameter, but you can read it as beta, the deformation variable. Beta equals 0 and beta equal 20 in some units. And you have a flat bottom in the potential and then a steep rise. It's not exactly a square well, but if you go from 150 at the phase shape transitional point towards a more deformed nucleus, 152 neodymium, that is this brownish line here, what changes? The outer wall doesn't change at all. It stays at the same position. The inner wall increases to a larger values of beta. Okay, so we didn't have an inner wall yet, but now we produce one.
How do they measure these things?
That was calculated.
Calculate.
That was calculated. Don't let me go into this because then I cannot finish my lecture, but I want to finish this.
Okay.
That was just the motivation for changing now my potentials. We have had, before, we had an infinite square well potential going from deformation variable 0 to a finite value beta w. Now, we have seen that in order to describe more deformed nuclei, we should better change the location of the smallest possible values of beta. So we take away also some parts of the parameter space in beta at small values of beta. So we have an inner wall at beta small w, or beta smaller. Here in these slides it's called beta smaller, okay? So, so now the wave functions are confined only in here. Here's infinite, the wave function not allowed. The wave functions must only live inside here, in this pot. And now there appears a parameter, namely, we can change the location of this inner wall with respect to the position of the outer wall. So we look at this ratio, the position of the inner wall, beta smaller, over beta width, beta wall. And of course this is always smaller than this one. That can range from 0 when we are in the x5 situation where the inner wall is at 0, and it can go up to 1, not exactly 1, but close to 1, which would be then the rigid rotor, because then we have a delta function in beta. So as a function of this ratio, we can now span the entire range from the critical point towards the rigid rotor limit. That is a whole, right? We have a wide potential at the critical point, and if we close our potential, we come to the delta function situation, that is a rigid rotor. So we should have all the potentials inside in order to describe this evolution from the critical point towards the rigid situation. We only have to solve this. Now it's a new potential. We have to solve it again. Okay. So here are the wave functions that would be allowed in this potential. So the lowest ones that have no node, or the first node at this outer wall, higher excited wave functions that have one node inside, here the second node is at the wall, or higher and higher and higher numbers of oscillations that correspond to higher excitation energies. Okay, so inside this allowed area, we still have the Bessel equations, right? Because there nothing changes, nothing changed. The only thing that has changed is there appeared a new boundary condition. Now the wave functions have to be 0 at this beta value, right, where the potential starts. New boundary condition means new conditions to the eigenenergies. So now we need the Bessel functions of second kind, right, that I have shown you before, because the solutions to this Bessel equation here will be superpositions of, in general, of Bessel functions of first kind and Bessel function of second kind with some amplitude gamma y. Right? Gamma y depends on the angular momentum state, depends on this parameter, which I call here this ratio of betas, R beta. Okay, R beta is the parameter of this model, which is because it confines the wave function in a certain range of beta. It's called confined beta soft rotor. Okay, so the new boundary condition at beta smaller produces a new energy quantization, which I will do now, and you will calculate in the exercises. So again, here you have the Bessel functions, and here now this Bessel function of second kind, which started off at a different value, a minus infinity for the variable equals 0. If you combine them, you can produce a 0 at any position which is required by the potential that you have taken. So you choose a potential, you choose an R beta, which gives you an outer beta W, an outer value of the wall, an inner location of the wall, and that determines what amplitude this Bessel function of second kind must have in order to have at this position this sum of first and second kind of Bessel functions to make a 0. Okay, so this is shown here. So you have now two boundary conditions. The wave functions must vanish at the outer value, and the wave function must vanish at the inner value. And the wave function is a superposition of Bessel functions of first kind and second kind. So you plug these z's into this equation here and put them to 0. Then you can solve for the gamma y in one equation and put it into the other. So for instance, you solve it for z smaller. Z smaller is when you put here beta smaller, or r beta times the beta wider. It's the same. So there is this condition here. This wave function at that value of z must be 0. So then gamma y is minus this ratio of Bessel functions of first and second kind at this location. You plug this gamma y into your equation and now use the other boundary condition, and that produces a new quantization condition. So that is this requirement from the boundary condition on the other side. So you have plugged this into here, used that boundary condition, manipulated the formula a little bit, and then you arrive at this quantization condition. So the Bessel functions of first kind at the outer wall times the Bessel functions of the second kind at the inner wall minus the Bessel functions of first kind at the inner wall times the Bessel function of second kind at the outer wall must be 0. So you can now search for those z's that solve this quantization condition, which again will be this constant, which contains the energy eigenvalue times parameters of the Hamiltonian. And they must be zeros of this new quantization condition. And then you can solve for the eigenenergies and you get this. Formally is the same structure as before. You have a constant times a square of a 0, but not of a Bessel function, but a 0 of this combination of Bessel functions here. That's all what changed. Can I have new virtual marker here? Okay, that means 40% of the potential are now forbidden. Thank you. Yes. And the wave functions have 60% of the original potential left. So how will the spectrum of X5 be modified when we do this? You can tell already from this. So when we go from R beta equals 0 to R beta equal 0.4, this doesn't affect at all the wave function of the first 12 plus state. Because the first 12 plus state that didn't live here in the space that we have forbidden now. It will not feel it. The ground state will feel it because we squeeze some probability of the ground state from small beta values into larger beta values. Which means that the energy of the ground state will increase a little bit, while the energy of the first 12 plus will not. Or we look at an excited zero plus state. So here we looked into the ground state band, wave functions with no node. Now we look at excited state with the same angular momentum. This is the ground state of x5. This was the first excited zero plus state which had a node. Because it had a node and it had to be orthogonal to the ground state, it will have higher probability at larger values of beta than the ground state, and also higher probability at smaller values of beta than the ground state. When we now make this region forbidden, that will affect the excited zero plus state even more than the ground state, because it lived there much more from, in the x5 situation. Right? So when we shift the wall from the inner wall to here, then we will squeeze more probability from the second zero plus state into this higher deformation region. So we expect that higher and higher excited states, I mean with more and more nodes, will be affected more and more strongly by changing the position of the inner wall. Right? Okay, and that is how the spectra evolve. Here you see 3 spectra calculated for 3 different values of R beta. Do you all remember what R beta is? R beta is, so here you have beta, is the position of the inner wall, that is beta smaller, to the outer wall, that is beta W. So R beta is beta inner wall divided by beta outer wall. Okay? So 0 means the inner wall is at 0, that is the x5 solution. 0.2 means 20% of the region are cut away. 0.4 means 40% of the region are cut away. So let's first look at the first 12 plus. The first 12 plus, we said, will not be affected strongly because it didn't live in the region that we have cut out. And these are absolute energies, yeah? And you see, they stay at the same positions. The 12 pluses are always at the same. The ground state will be affected a little because it lived also at this forbidden region then. So here it is low, here it is about at the same position, here it's increasing already. Okay? So the higher the spin is, the less it will be affected. That means when you increase R beta, you shift this wall, that the 0 plus comes closer to the 2 plus, while the 4 plus is less affected. And if you take the R4-2 ratio, that is this distance divided by that distance, that this will increase because this will become more quickly smaller than this one. So, and that is what you observe. You go from R42 2.90, which is x5, to 3.10, to 3.29 already in this case, eventually to 3.33. So when you close these walls, you are at 3.33, rigid rotor. So now, as a function of one parameter, we can evolve the spectra from the critical point to the rigid rotor. Yes, you have a question? No. Okay, so that was the first thing. Second thing, excited states with more and more nodes. Okay? Let's take at the 0 plus with 1 node. That is this one, this beta band. In x5, R beta equals 0, it's close to the 6 plus. When we close the wall, so we shift the inner wall to larger values, it has states with more nodes will be affected more than states with 1 node. So all these, the ground state band has no node, or only, I mean, a node at the boundary, at the outer boundary. This one has 1 inner node, so will be shifted up more quickly. This one here, the third 0 plus state, so S equals 3, will be shifted more quickly, goes up to high energies more quickly. Right? So the locations of the 0 plus close to the 6 plus at x5 move somewhere between 6 plus and 8 plus at some values of R42, close to, and is shifted to higher and higher energies. Here is already above the 10 plus state. So as a function of R42, the excitation energy of the first excited 0 of the beta band, I mean the band that has a node in the wave function in beta, will be shifted to higher and higher values. And again, the model correlates now these numbers. So the R42 ratio and the R02 ratio are correlated by the model, uniquely correlated, and that is the red function, the red curve here. That is the prediction of the model as a function of R beta, which is now goes from 0 to 1. You can, for every R beta, you can parameter-free calculate the alpha-2 ratio and the R0-2 ratio and make a dot. And when you connect the dots for the range of R beta going from 0, that was x5, to infinity, then you get this red curve. So here's 0.4 already, and it exactly follows the data. So that is a sort of the, at least it's satisfactory. Okay, so this model is somehow living between the critical point and the rigid rotor. That is a structure triangle, a picture, how or where we locate the structure of nuclei in terms of the geometrical model. So this corner here is the quadrupole vibrator. This corner here is the rigid rotor limit, where you have this rigid moment of inertia as a function of angular momentum. And this is the gamma unstable case, where you have soft triaxiality, which maybe I will discuss later, but I don't think I have time. So we were discussing this region here, which is from the shape phase transitional point between a vibrator and a rigid rotor, the X5 solution, towards the rigid rotor. So that is the region where this confined beta soft rotor model can work, or can be applicable. So let's look at data. I have shown you before the data for this Bose 164. Here's the rigid rotor. We have seen the deviations, I mean at the 10 plus, so that was normalized to the first 2 plus here, right? And 10 plus, there was already a deviation of, let's say, 10% or so. And here I have shown you the values for the confined beta soft rotor model, where I fix this parameter R beta to the alpha-2 ratio. So I make sure that the 4 plus and the 2 plus data are the same as in experiment. And everything else is prediction. Right? That is parameter free. So you see the 6 plus 501.3 kV, 501.4, 8 plus 843.7, 843.5. 200 electron volts difference. 1261.3, 1260.7, 600 electron volts. 1745.9, 17, well, zero.
So I'm a little confused how the fitting was done again, because I thought you needed the ratio of 0 plus to 2 plus to fit your moment of inertia. But
Correct, correct. So I need the ratio of 4 to 2 in order to fit R beta. And then I need a scale. And the scale, so with the scale, here I give now energies in keV, so I have a scale. So you can say I fix the R4-2 ratio, then I get R beta, that is what you will do in the afternoon. And then in order to get the scale, I just fix this scale. I multiply everything by 73.4 keV, and then I get these numbers.
okay.
You do the same for uranium-236 that I have shown in the beginning. So now I must go here to the 4th digit in order to, because the description is so precise. So I fix these two numbers, and then I predict 309.9 for the 6 plus, 522.2 for the 8 plus, which is again exact, 782.0, 300 electron volts difference, 1085.0, 1085.2. It's absolutely amazing how well this works. Yeah.
Maybe I misunderstood something, but in the first example, you said that first you use the ratio 4 plus to 2 plus in order to get your R beta, and then you fix all the level according to the 2 plus. But then shouldn't be the 2 plus energy, of course, is exact.
Yes.
I mean,
Yes.
you just
And the 4 plus energy also.
Yeah, but I was expected, but it's not the case.
Yeah, because I've cheated, I have then fixed it here and then it doesn't matter. I mean, so it's in the 4th digit. So I fine-tune it in order to let it look even better, but I mean, it's just the KV.
What about the first excited 0 plus?
You don't know the beta band there. It will be already. It will not be experimentally the first excited 0 plus state. It's already, these are strongly deformed nuclei. So this beta band will be already in this nuclei, let's say from the prediction at 2.6 MeV or so. So you don't know.
It only works for the ground band.
It only works for the ground band in these rotors, because there I think the beta band has never been seen. The beta band is up there. It's not the first excited 0 plus then. It will not really be because it's squeezed to too high energy already. In this, so the CBS works best for the ground band in these nuclei that are strongly deformed, because the deviations from the rigid rotor are so small, and that I can get them very well by letting the potential have a little width. Well, the width is not so small. Actually, our beta is 0.4. Right? So you have 60% you have still left of the X5 potential. But the deviations are smaller than 1 over 100, 1 over 8. I mean, that's really remarkable. You can do this for all these nuclei. This is the relative deviation in the ground band, and over the ground band up to the backbending region or so. It's of the order of 10 to the minus 3. Think about the Balmer series, the famous Balmer formula. 1 over n squared minus 1 over 4, how quantum mechanics was found, is good to 10 to the minus 4. Not much better. Okay. But actually, the most so we have an analytic solution for X5, we have an analytic solution for the rigid rotor, which is a rigid rotor, and we have this confined beta soft rotor model, which is now analytic between these things. The most interesting for this model is, of course, something which is far away from X5 and far away from the rigid rotor. So nuclei that have R42 ratios between 2.9 and 3.33. So 3.1. Right? 3.1 is the most interesting for these. And if you look in the nuclear chart, this is some piece of the rare earth region, dysprosium up to hafnium tungsten. Then you see that for these nuclei, dysprosium 158, erbium 160, ytterbium 164, hafnium 168, they have R42 ratios of 3.1. So therefore, I've shown you in the beginning erbium 160. We have done experiments on this. I mean, that was a couple of years ago, 8 years ago. So we have done gamma ray spectroscopy. I have shown you the data. There is this ground band. There is the excited 0 plus band. So you see the 0 plus already above the 6 plus. And there is also a gamma band. We have done some work on spectroscopy. I will not go into this. Here is the evolution of these structures in erbium isotopes. These are the ground bands from erbium 156 to erbium 164, and here's in the middle is erbium 160 that we are interested in. Here's erbium 160, that is the gamma band, K equal 2, and here's the shape phase transitional point. The 0 plus is lowest, but this is erbium 160 already beyond the shape phase transitional point. And we have extended these bands in order to do this comparisons. And now comes the interesting thing. So you have seen that this model, because of this open potential, that produces as a function of angular momentum, produces centrifugal stretching. So this is the ground state wave function that you have seen before. And when you look then at the wave function of a higher angular momentum state in the ground band, you will see that was the 12 plus, that the wave function has shifted its probability to larger values of beta. That means the higher you spin it, it's more probable that it elongates, which you expect also from that. I mean, you spin a bubble of water in the ISS, I mean, then the higher you spin it, the more it will elongate. You know, that is the balance between the centrifugal and forces and the surface tension. So you have centrifugal stretching, and that means that the higher spin states have a larger moment of inertia. And you can then take this look at the moment of inertia from these energy differences between the states and compare them to the lowest in the band. So this is moment of inertia from the band head plus 2. So from any state in the band compared to the moment of inertia of the lowest state in the band. And you end up with this formula when you plug in the rigid rotor value. So when you plug in the I have to write it up.
Don't go too far out to the right, to the left. You'll be off the movie.
So the energy of a state with angular momentum J in the band K is the energy of the band head plus h bar square over 2 theta times jj plus 1 minus kk plus 1. Okay? And if you use this formula in order to get theta k of, so this must not be a constant but can vary as a function of angular momentum. So when you have these energies, you can take energy differences and solve for this theta k, for the moment of inertia, for every state, and then you get rid of, you take relative values, and in the rigid rotor, you would expect that all these moments of inertia are equal, right? So then you give this ratio is always 1 and constant. The black dots are the data, and the green lines are the result of the confined beta soft rotor. This is for the ground state band. So this is 1 at angular momentum 2. So at the first 2 plus, that's the 2 to 0 gives you the first moment of inertia. So here it is fixed to 1. And then in the data increase, the rigid rotor would stay at 1. So it would be a constant here, flat. No centrifugal stretching. And this CDS model with centrifugal stretching gives the green curve. And because we had a very good description of the energies, it follows the data. But it follows the data not only for the ground band. Here, that is in the transition region, we also have the excited beta band, we have the gamma band. We can do the same for beta and gamma, and there's some staggering in the gamma band, but also there the centrifugal stretching is described very well by the model. So that means all these bands stretch alike, because it was one parameter, R beta, one potential, that describes the stretching. I had to take relative values because the moments of inertia, they are not described correctly. The model gives much too large expanded spectrum. I have to take relative values in order to show the centrifugal stretching. The absolute values don't agree for the excited band. For the ground band it agrees, but for the excited band it doesn't. Moments of inertia are important. So there's a systematic increase of the relative moments of inertia, so that is centrifugal stretching. And the spin dependence in the ground beta and gamma band are well described in the confined beta soft rotor model with one parameter, which is adjusted to alpha 2. So all bands stretch alike. That was 160 erbium. The other example was 164 ytterbium and 168 hafnium. So for ytterbium we have done the same, spectroscopy, ground band, beta band, gamma band. There's an evolution of bands. 164 ytterbium, that is our nucleus here, this one. So here's less deformed, here's more deformed, so the spectra are compressed. And 164 ytterbium, this is our nucleus, and it's a beta band here. And we do exactly the same, centrifugal stretching. Again, the red curve is a CBS fitted to these 2 points here. And everything else is prediction. The beta band, well, there are some deviations, but it's not so bad. And the gamma band also very good. But you will learn this model in the afternoon. You will also get as a gift, you get a code which you can use to calculate your own nuclei. Then you want to look at, this was energies. You want to look at transitions. E2 transitions, for instance, the E2 operator is alpha 2 the quadrupole variable, plus if you really want to make sure that there is a well, you can expand it in alphas. There's a higher order term. Usually this is confined to the first term only, but I want to use also the second term. When you go into the intrinsic frame, you have a piece with a first order alpha, which produces a piece in first order in beta, and the second order alpha produces a piece in second square in beta. So you have an effective charge in front, and then a piece which is proportional to beta, and another piece which is proportional to beta square with another constant chi. I want to use this form because this is consistent and comparable to the interacting boson model that you have heard about yesterday, where the E2 operator, TE2, is an effective charge times the quadrupole operator that contains a chi. And this is an effective charge times, in terms of bosons, that was S dagger D, 1D boson plus D dagger S, so either you create it or you annihilate it, plus a term chi times D dagger D. So when you have Capriopietralla, of course, so you have a piece, these D boson operators, there's one D boson in here. This compares to a term which is proportional to beta. And then we have a term in the quadrupole operator which has two D bosons, and that corresponds to a term which is proportional to beta square. And you have this parameter in front. So this is now exactly the form I have here, apart from that I take here a scale out. But that is fine, I just plug it into the effective charge. Okay. So then you have the wave functions, and you can calculate E2 transitions. And
Excuse me.
Yes.
I'm not following why the proportionality to beta is linked to these creation and annihilation operators.
Well, that would be a lengthy argument. Look, in the interacting boson model, these D bosons, they describe this quadrupole deformation oscillation set, and you can show that the number of D bosons in the ground state is proportional to beta square, to the square of the quadrupole deformation, which is not exactly, which doesn't show you directly that D tilde is sort of proportional to beta, but when you go to the coherent state, I hope this is right, then you can show that the effect of D and D dagger is that being proportional to beta.
Mark Caprio talked about the coherent state formulas the other day and showed the formulas that kind of motivate that relation.
And Young showed it.
And Young.
Okay, so here are comparisons between the CBS and Samari 152 for BE2 transitions, and Samari 154 in the CBS. There's no comparison to X5 because it's already deformed, so more strongly deformed, far away from X5. And you see, on average, a very good agreement also for the BE2 variants. Well, here there were no data, and well, in the excited bands, I mean, there was also little data only, but small things are small, and something a little bit larger are a little bit larger.
So to do these calculations,
Oh, you have the wave function.
right? Yeah, that's what I was going to say.
You
Was
plug in the operator.
it straight up integration.
You integrate,
Okay.
and you do this also in the afternoon. Yeah.
And don't get what is beta M?
Our beta M is beta W on this. I
Okay.
mean, this was a. I have collected presentations from years, and then one year it was beta W, or 1 year was beta great maximum. That was a big M, maximum, the maximum. And there was a minimum at a small m. Yeah?
Why is there no prediction for the last transition?
Good question. Maybe we were lazy at that point. I don't remember anymore. That was years ago.
You mean the experimental value?
CBS, I mean here, there's a value missing here. I think, there's an error on the table. I mean, this number ought to be here.
Error.
There is no error.
Yeah.
That was the theory. So you see also that goes up. That is a 2 to 4 and 4 to 6. In always the spin up things, they are relatively large. So this is supposed to be there. Okay, so that means from BE2 measurements, from lifetime values, you see the stretching in the bands. Well, I stop about here. That is from lifetime measurements, you get the transitional quadrupole moment. You can plot it as a function of spin. So this goes up the band. That is from the 2 to 0. It's normalized. Here would be the rigid rotor. The green curve is the confined beta soft rotor model, and you see the stretching of the states. The 4 plus has about the same transitional quadrupole moment, which you get out of the BE2, as the first 2 plus. But the 6 plus, with some errors, has already a larger transitional quadrupole moment. So the wave function stretch. The 8 plus has an even larger transitional quadrupole moment, and the 10 plus even further. And the green curve is the CBS model, and you see how the wave functions stretch, centrifugally stretch. The quadrupole moment gets larger and larger and larger, the higher you go up the band. Same set of data for hafnium 168. This is energies, relative moment of inertia. So red crosses are data, green is the CBS model, and here's transitional quadrupole moment. These are the data for the 4 normalized to 2 plus, of course. So here 4 plus has a larger, 6 plus even larger, 8, 10, and these faint lines is the CBS model. Okay, 170 hafnium the same. At this point, I think we all want to have coffee. I will stop and I will not discuss the application of this confined beta soft rotor model to a situation where you have gamma independence. But of course you can do this there also. In the derivation of our formulas, I have assumed a decoupling of beta and gamma variables, which means I have treated the gamma degree of freedom as a harmonic oscillator with some high excitation energy, which would not influence then the beta wave function. But I can also obtain a solution where the potential in gamma and the triaxiality is completely flat, the potential is independent of gamma. That produces the O5 symmetry. And in this case, I can also then treat the beta variable independently, and that is this O5 confined beta soft rotor, which describes also, of course, the evolution of 0 plus states that would cross as a function of R42. But this would have been another for mixed symmetry states. Again, I will show a lot of experimental techniques, and relate them to the theoretical predictions. And then I think I will do a little bit about microscopic description, and give you experimental evidence for the mixed symmetry character. There is a very nice review article by one of the organizers, and others that I can recommend to read. That was already some time ago, in 1986, but still very nice literature. So, you have learned about the interaction boson model. Here we consider the nucleons in the nucleus as paired in pairs, and they are approximated by bosons. And then you use for a certain nucleus in the nuclear chart, the valence particles, so valence protons and valence neutrons, with respect to a nearest doubly magic core. So you use only the valence space dynamics, and you approximate these pairs of protons and pairs of neutrons as neutron and proton bosons. And then you write up a boson Hamiltonian, which consists of boson energies, boson-boson interactions, and in principle higher order terms. In order to keep it simple, usually one neglects higher order terms. And I will discuss mostly only systems where we confine ourselves to monopole bosons and quadrupole bosons, the S and D bosons. In the end, I will maybe discuss a little bit about octuple bosons also. So, for a given nucleus that you consider, you have a fixed number of valence protons and valence neutrons, and that means the number of proton bosons n pi and the number of neutron bosons n nu are separately conserved and constant for a given nucleus. And you have these S and D bosons. They produce, as Professor Joly has discussed yesterday, a U6 structure. So you have one M substate of the S boson, 5 M substates of the D bosons, which is angular momentum 2. In total, 6 M substates, and they form, produce such a U6 structure. You have now a U6 structure for the proton bosons, a U6 structure for neutron bosons, and you couple them. That gives a very rich structure, group structure here, and I will discuss one limit of that structure, which is particularly simple. So, first takeaway message is the interacting boson model 2 is an interacting boson model for proton bosons and for neutron bosons, in which proton-neutron interactions in the valence shell are treated explicitly. So you can write also the Hamiltonian as a Hamiltonian which contains proton bosons only. That is of the type of interacting boson model 1, so only one type of bosons, so then you can neglect the index of whether it's proton or neutron. So it's just a boson Hamiltonian as was discussed yesterday. The same for neutrons, like an IBM 1 type Hamiltonian for the neutron boson, but then there appears also a proton-neutron interaction, which is now a sort of new in this model, and more realistic, if you want. So a simple Hamiltonian that you can consider, out of the many possibilities you can write one boson energy terms and boson-boson interactions, is this Hamiltonian here, which is a sort of pairing plus quadrupole Hamiltonian where you consider also symmetry energy term. So you recognize some pieces from what you have learned yesterday. So you have the number operator of D bosons, now for protons with the proton D boson energy, a number operator of D bosons for neutrons with the neutron D boson energy. You have a quadrupole interaction with some strength. So you can have proton quadrupole times proton quadrupole. You can have neutron quadrupole times neutron quadrupole with some strength. And you can have a proton-neutron quadrupole interaction with another strength constant. And then a term which is called the Majorana interaction, which measures this exchange symmetry of the wave functions with respect to protons and neutrons. I will come to this in more detail later. So here are again a reminder to these operators, the D boson number operators, and D now rho, you can either have protons or neutrons, is just the sum of M substates for the D bosons of that particular isospin rho. So you have D dagger D and sum over all magnetic substates, or you can write it in this scalar product form, D dagger rho dot D tilde, which I hope was introduced. Was it D tilde? So these are the D boson number operators that are here, and here are the quadrupole operators, and we have discussed them already in the previous lecture briefly here at the blackboard. So it's for each isospin, it's S dagger D tilde plus D dagger S plus there's an additional term where you have D dagger D. coupled to angular momentum 2. Quadrupole is angular momentum 2. And then the Majorana operator, that contains pieces. This is in normal ordering, so here you have two annihilators always a term with protons and neutrons. And here you have the same terms with creation operators. And then d dagger pi d dagger nu times d pi d nu coupled to angular momentum k, where k is odd, 1 or 3. These odd tensor products are antisymmetric when you exchange the labels. So when you do d pi d nu coupled to 1, this is minus 1 of d nu d pi coupled to 1. So these are the antisymmetric terms. Also, you observe, if you would consider a nucleus with only one type of bosons, let's say only proton bosons, 0 neutron bosons, then this interaction here, because here you always have a neutron boson annihilator present, and they annihilate the vacuum, so that would be 0. So the effect of this operator would be 0 if you have only one type of bosons. And then this Hamiltonian reduces to the ordinary interacting boson model 1. And the value of this symmetry term would be 0 in that case. So this is interesting for the usual case where you have both valence protons and valence neutrons. So when it would reduce to interacting boson model 1, then you get this structure again. You can solve this Hamiltonian, this IBM1 type Hamiltonian in these three dynamical symmetries, U5, SU3, and O6, and depict it again in this sort of symmetry triangle, custom triangle, with these three analytical solutions. And you have here the vibrators, here the rigid rotors, and here the gamma soft nuclei. I have discussed in the last lecture, I have discussed this leg here for the deformed nuclei. And there's also a line here which depicts this shape phase transition from spherical nuclei in this region to deformed nuclei in that region. Okay, but now we consider a nucleus that has both valence protons and valence neutrons. That is the topic of this lecture. Now let's make it very simple. Consider an even nucleus with 2 valence protons and 4 valence neutrons. Think of tellurium 106. So you have 6 particles out of tin 100. So you have 2 protons go from tin to tellurium, and you have 4 neutrons go from tellurium 102 to tellurium 106. So then 2 valence protons make 1 valence proton pair, which means 1 proton boson, and 4 valence neutrons make 2 valence neutron pairs, that means 2 neutron bosons. So you have a nucleus with 3 bosons. And we can make this Hamiltonian even simpler. It's just for pedagogical reasons. So we use these constants here, all 0, and here are also constants in this operator. We put them all to 0. We only keep this term here, okay? So, and then, just in order to do a calculation, we put as a neutron d boson energy 1 MeV, proton d boson energy a little bit different, a little bit higher, say 1.3 MeV. Let's look at the spectrum of this Hamiltonian. We can predict it already.
Why would you put more energy to the proton?
Well, if I would do it
When
equal,
you have some code, it would be maybe
no.
even lower.
It's just to introduce the things. If I make them equal, then something else happens, and this I will discuss later. I just want to do it different. I just take this from the sky. Okay, it's just my choice.
Okay.
So I want to separate the things. So let's look at the solutions for this Hamiltonian. What state will be the ground state? We only have S bosons and D bosons. And we have 3 bosons. If one of them will be a D boson, that will cost energy. If it will be a neutron D boson, it costs 1 MeV energy. If it will be a proton D boson, it costs 1.3 MeV energy. So the lowest energy state will be the state which has no D bosons. That means only S bosons. So we have 2 neutron bosons, 1 proton boson. That means a neutron S boson, a neutron S boson, and a proton S boson. 3 S bosons, angular momentum 0, you can couple them to angular momentum 0 only. Right? So you have a 0 plus state. That's the ground state, the lowest energy state. Now the first excited state you can make is the one where you have, now you must transform 1 S boson into a D boson. The proton D boson is not so good because that costs 1.3 MeV energy. So you first take a neutron D boson. So you have 1 neutron S boson, another neutron, and now a neutron D boson, and a proton S boson. Which means angular momentum 0 times angular momentum 2 times angular momentum 0 is angular momentum 2. So we have a 2 plus state. And this 2 plus state is a neutron excitation. And that occurs at 1 MeV energy, because you have 1 D boson at 1 MeV. Or you can do a proton D boson, but that costs more energy. So the wave function here is as nu D proton. Right? So this is again a 2 plus state, which now occurs at 1.3 MeV excitation energy. I just chose these parameters in order to split them. Then you have 3 bosons. You can have instead also 2 D bosons, which costs more energy, of course. Now it's cheapest if you take 2 neutron D bosons. That costs you 2 MeV in total. And now you have 2 identical bosons that of angular momentum 2 that can couple, that must form a symmetric wave function because they are bosons. So they can couple only to even spins, 0 plus 2 plus 4 plus. So you get this famous 2 phonon triplet, 0 plus 2 plus 4 plus, at excitation energy twice the energy of the first 2 plus state. Okay, or you make a higher excitation, you use 1 proton D boson and 1 neutron D boson, and you keep the third as an S boson, which would be a neutron S boson here. So now at 2.3 MeV excitation energy, 1 here, 1 there, you have a new multiplet of states that are formed by a neutron D boson and a proton D boson. But now these bosons are different. And now you can couple them also antisymmetrically because they're different. And you get the full quintuplet of states, 0 plus 1 plus 2 plus 3 plus 4 plus. And there would be a state which I haven't plotted where you have 3 D bosons then. But the important thing is here, so you can tell already from this Hamiltonian, you know the wave functions, you know the excitation energies, and you know that there appear antisymmetric states with respect to proton-neutron wave. And now comes your question about the equal D boson energies. Why I have done this just to introduce this example.
No,
now
my
suppose
question was
equal
other.
D boson energies. Now you were thinking about Coulomb repulsion and they cost more energy. Well,
I would put them other way around.
oh, you think the proton D bosons are lower in energy than the neutron D bosons? Is that what you
Because
think?
they have cone proportion.
Well, it depends so much on the shell structure. Think about these microscopically, they are formed by particles in the shell model, sitting in shell model orbitals. Okay. And then you can have different gaps to other shell model orbitals. So you can have different excitation energies for making an S boson into a D boson. They can have different energies for neutrons and protons depending on the underlying shell structure. That can vary through the nuclear charge. So sometimes you can have equal D boson energies, sometimes this can be lower, sometimes that.
Okay.
But these are phenomenological constants that you have to fit to the nuclear region that you want to describe.
So I look where I am in the shell and then figure out what's going on
In
there.
principle, yes. But the problem is that doesn't really work that way so well. I mean, accurate enough. I mean, the best way is just to fit the Hamiltonian, to fit the constants to the data of the nucleus you want to describe. Okay, so now we make them equal. That means the proton excitation and the neutron excitation occur at the same energy. And when they occur at the same energy, I have split them up a little bit in order to see the difference. So there's a neutron 2 plus state, a proton 2 plus state. So any proton-neutron interaction would mix them. Well, that can mix them, of course, 2 pluses. And if you mix them, that means they will split up into a symmetric combination and an antisymmetric combination. That's just two states mixing. Yeah? So you have psi 1 plus psi 2 for the lower solution and psi 1 minus psi 2 for the higher solution. You have discussed the two-state mixing. Okay, and so for exact degeneracy, when you have chosen identical excitation energies of the initial configurations, any PN interaction leads to this symmetric antisymmetric wave function. And that means you get exact degeneracies of these states for equal parameters in the Hamiltonian for protons and neutrons. So if you use here equal parameters for the proton and neutron d bosons, and here for the quadruple operators, then you get this symmetric and antisymmetric pieces, wave functions. If you have, so then you can consider the bosons also as being identical, only having an internal variable, the isospin label, proton or neutron, that distinguishes these identical bosons. So we can apply here the isospin concept of Heisenberg from the 1930s. So for identical proton-neutron parameters, the proton-neutron bosons are identical particles with an internal distinction, a label. So you can apply this isospin concept, and that reduces, so this is a constraint, of course, to all our possible interacting boson model 2 Hamiltonians. But if we do this, that reduces the complexity of our group structure, u pi 6 times u mu 6, to a spin group times u6 for proton and neutron bosons. So formally, we introduce this boson isospin, like this isospin for nucleons, neutrons and protons. We have a boson isospin of 1/2, where we define the proton bosons to have the projection plus 1/2, and the neutron bosons to have the projection minus 1/2. Okay? And then you can, for a multi-boson wave function, you can couple these isospins to a total boson isospin. And this boson isospin is called F-spin because we use this sign F here. So we do spin 1/2 coupling. So let's look at, think of spin 1/2 objects, you know, two spins 1/2 electrons, and you couple them. So you have the first spin 1/2, the second spin 1/2, and you do product states. You can couple them either to angular momentum 1, then you have an M substate where the first particle has a spin up, the second particle has a spin up, is M projection plus 1. You can have both pointing down, M projection minus 1, or you know how to do these ladder operators. You have the first up, the second down, plus the first down, the second up. So this is symmetric under the exchange of the indices 1 or 2. Or you have the antisymmetric combination, where you couple them, well, you know how you must do this. You must have a wave function which is orthogonal to the other state with this angular momentum, with this M substate. So you have this antisymmetric piece with a minus sign here, which only occurs if particle 1 and particle 2 are different. If they are identical, then this is exactly 0. So you get this S equal 1, which is S max. All components contain symmetric coupling of particles 1 and 2. And you get this S equal to S max minus 1, which in this case is 0 here for two spin 1/2 particles, which is antisymmetric under the exchange of labels 1 and 2, and which is only non-zero when 1 and 2 are different. Okay, so you can do, you can form these F-spin operators. I just defined these operators, a raising operator. So remember, proton bosons had an Z projection of the F-spin plus 1/2. Neutron bosons have minus 1/2. So you can increase the Z projection of the F-spin when you transform a neutron boson into a proton boson. Then you have M substate from minus 1/2 to plus 1/2. So an operator that transforms a neutron boson in any quantum state into a proton boson in exactly the same quantum state is a ladder operator for the F-spin. Right? So then you write this, an operator that transforms a neutron boson into a proton boson in the same quantum state. That means S pi dagger S nu, you annihilate a neutron S boson, create a proton S boson. Or the same for D, you annihilate the D's in all the substate and create exactly the same substate of the proton. This is the raising operator. The lowering operator is if you do it the opposite. So you annihilate a proton and create a neutron. And in order to have a spin algebra, you have a ladder operator going up, a ladder operator going down, and a Z projection. What is the Z projection for the F spin? Well, you count the number of neutron bosons, multiply it by minus 1/2. You count the number of proton bosons, multiply it by plus 1/2. Then you have the total Z projection of all the bosons. Okay, so that is ND, that is NS. The number of D bosons plus the number of S bosons is the total number of bosons of that type. So you have the total number of proton bosons here, you have the total number of proton bosons there with a minus sign in front. So this is 1/2 N pi minus NU. This is just, you count the difference of neutron bosons and proton bosons. So this is the Z projection. Now, when you can calculate the commutators of these operators, and you find these commutation relations that are exactly the commutation relations of angular momentum operators. So you deal here with a spin. So the F-spin operators exhibit spin commutation relations. So that is a group SU2 for F-spin, and hence the name F-spin. It's like a spin. So a spin has an invariant, right? S squared. That is this Casimir operator, which you can write in these ladder operators that I had before. There is a lowering operator times a raising operator plus Z projection times Z projection plus 1. And it has two quantum numbers. So you apply this S square operator to your wave function, then you get S plus 1 times the wave function. You apply the Z projection to the wave function, then you get the M quantum number times the wave function. So these are diagonal in the wave function. And correspondingly, for the F spin, you just produce, and that was just a reminder, you know this. And you have these ladder operators also for the F spin, so you form this F square thing, just in analogy to the spin case, so F minus times F plus the Z projection operators, which I had on the previous slide. And then you know that when the wave functions have good F spin, that when you apply this operator, you get F plus 1, and you get the wave functions back. With the boundary conditions, of course, that for the Z projection, the F spin is always at least as large as the Z projection. Right? The projection can never be larger than the total angular momentum. And the F spin cannot be larger as the number of bosons times 1/2, because it can only if you have one sort of bosons, so n proton bosons, you have n times 1/2. That is the maximum F spin you can have for n bosons. So this F spin is always between F max, which is half the total number of bosons, and 1/2 times the difference of protons and neutrons. Okay, so now let's look at an example, 2 bosons only. 2 bosons only, and now you can distribute them over proton and neutron labels. So either you have no proton bosons and 2 neutron bosons, then you have the Z projection of the F spin, which was given by 1/2 times n pi minus nu. So 1/2 times 0 minus 2 is minus 1. So Z projection is minus 1. Or you have one proton boson, 1 neutron boson, then Z projection is 0. Or you have 2 proton bosons, but then 0 neutron bosons. So Z projection is 1. So then, when you look at the spectra, so here's excitation energy, as we have done this before, you put a simple Hamiltonian and have a 0 plus ground state, and then a 2 plus state, and these sort of things. Then, in this case, you can have symmetric couplings only. So, for instance, no 1 plus state. But here, when you have different bosons, then you can also have antisymmetric couplings, and new states appear. They appear only in this example because this is the only column where there are different bosons here. So you see like spin multiplets, these states here have F spin 1, and these new states that appear that contain an antisymmetric piece that can only occur when proton and neutron bosons are available, they have non-maximum F spin. In this case, they are F max minus 1 states because they have only projection 0. So you have F spin 1 states and F spin 0 states, or F max states and F max minus 1. And I'm talking about these states that contain antisymmetric pieces, these mixed symmetry states. Aha, there's mixed symmetry. So F max states, they correspond, of course, to IBM 1 because they must be a sort of identical. They contain, they belong to a multiplet where you have states that contain only one sort of boson. Let's say proton bosons only. But when you have only one sort of bosons, you can neglect the label. That is that IBM 1. So the F max states, they correspond exactly to IBM 1 state. And if proton and neutron bosons are present, then the wave functions can contain antisymmetric coupling. And you have non-maximum F spin, these purple states, and these are called the mixed symmetry states. Okay, so when is F spin good? We have discussed this yesterday with Professor Joly, when these quantum numbers are good. That is when this operator F square commutes with H. And it commutes with H, for instance, when you have equal parameters for protons and neutrons. So you write these operators symmetrically and then give them a common constant. And then you can write this operator that measures the symmetry as F max plus 1 minus F square. For symmetric states, where that means for symmetric states, you have maximum F spin, F max. So then the value of the F square operator is F max plus 1. So then you see that this exactly cancels. So the Majorana operator that I have used before has no effect, has 0 for symmetric states only, and is finite for states that have a smaller value of F spin than F max. Right? So for the mixed symmetry states, it is fine. And if the raising operator commutes also with H, then you have for a certain, you have an eigenstate of the Hamiltonian with some eigenenergy E. Then also the raising operator applied to psi is an eigenstate of H with the same energy, right, because they commute. And that means that you have in a different nucleus now, because the raising operator transforms a neutron boson into a proton boson. So you go from one nucleus to the other. You have the same energy, so you have isospectral nuclei, because here this eigenvalue stayed the same. So you go from one nucleus, you apply the raising operator, go to another nucleus, where you have identical excitation energies. So these are the so-called F-spin multiplets. This is shown here. This is data. This is data for nuclei that have the same number of bosons, 12 in this case, but distributed differently on protons and neutrons. So dysprosium 156, 8 proton bosons, 4 neutron bosons. Erbium 160, 7 proton bosons, 5 neutron bosons, 12 again in total. Ytterbium 164, these are the same nuclei that I have discussed before in this confined matter soft proton model. 6,6, ytterbium 164, 5,7, hafnium 168, 4,8, tungsten 172, 3,9, osmium 176. So it goes all the way to mercury 184, which is very close already to lead. So there are two, mercury has Z equal 80. So it's 2 protons from a closed shell apart, and there you start to see deviations. So what you are supposed to see is that with a very good approximation, I mean, many states have exactly the same energy. There's something funny going on with the 0 plus. Now you can say, okay, there are some deviations, so this is not a very good description, but that ranges from mass 156 to at least to 180. Okay, so sort of 24 mass numbers. So if you look, for instance, instead in isobars that are very close to 162 dysprosium, the neighbor, even 162 erbium, 162 ytterbium, only 3 nuclei, you see much larger deviations. So this is not trivial. I mean that this F-spin multiplets occur. Okay, so takeaway message 2. The IBM 2 Hamiltonians that treat proton and neutron bosons equally, that means it commutes with F squared. The eigenstates can be classified by the F-spin, which quantifies the amount of proton-neutron symmetry in the boson wave function. And this F-spin is between F max and Fz. And the lowest states have F max. Okay, now let's consider another simple example. We haven't seen yet the antisymmetry. So now we consider this. Yes?
Somehow this state is strange. You said IBA 2 treats neutron and proton equally, but IBA 1, I think, also treats them equally.
Oh yes, yes.
So
But
it's kind of same state.
no, that simply means that the IBM 1 is contained in the IBM 2 that treats proton and neutron bosons equally. But in the IBM 2, additional states occur. And this I will discuss exactly now. So your question was at the right moment.
Okay.
So let's look at this example. You have now the Hamiltonian epsilon ND, where ND means ND proton plus ND neutron. So they are treated equally. They have one parameter in front, the epsilon. Plus a constant times this Majorana interaction, which has only, so we consider two bosons, one proton boson, one neutron. So this M can take two values only, 0 for the maximum F-spin and 1 for the non-maximum F-spin. Okay, now let's construct the eigenspectrum. Again, we have a d boson energy term, which costs energy. So the lowest state will have no d boson in it. So S pi S nu. That's a 0 plus state, which is symmetric under exchange of proton-neutron labels. So it's an F max state. So the value of this operator is 0. So that is at 0 energy. Ground state. Now we take one d boson. That costs energy epsilon, and it would cost energy lambda if the state would not be symmetric under exchange of proton and neutron labels. So you better make it symmetric in order to have a lower energy. And there's only one way. You have a proton d boson, neutron s boson, plus a proton s boson, neutron d boson. No other way in order to get a symmetric combination. And 1 over square root 2 in order to normalize the proton. So this is the first 2 plus state, which is called quadrupole excitation symmetric, QS. And then you can have the symmetric combinations of proton and neutron d bosons remember, when you couple two quadrupole operators, the coupling to even spins is symmetric under exchange. The coupling to odd spins is antisymmetric. So you want to avoid this punishment of this symmetry operator here. So you get the lower energies when you couple them symmetrically. That means to even angular momentum, 0 plus 2 plus 4 plus. You could also couple them to odds. You can also couple them to 1 plus 3 plus, but then they're antisymmetric. Okay, so this is your spectrum for the symmetric states. Ground state, the one quadruple phonon excitation, the two quadruple phonon. Symmetric triplet. Symmetric two quadruple phonon triplet. Or you do the antisymmetric things. So the orthogonal combination to this symmetric one is that with a minus sign. So you have d proton s neutron minus s proton d neutron. Creation operators acting on the vacuum. Or you have this antisymmetric two quadruple d two phonon couplings. So you get the 1 plus and 3 plus states. And this is a 1d boson state, so it's a 1 phonon excitation, which has this minus sign here, so it's an antisymmetric quadruple excitation. If you have more than 2, then you see that it only contains antisymmetric pieces, so it has some mixed symmetry, and therefore it's called the mixed symmetry excitation. So this is the mixed symmetry quadruple phonon excitation, that is a symmetric quadruple phonon excitation. And on top of that, you can do 2 phonon states with 2 d bosons here, and you have 1 plus and 3 plus states. If you have more than 2 bosons, you would have here the full quintuplet of states, 0 plus, 1 plus, 2 plus, 3 plus, 4 plus. Okay, so now you have seen what comes in addition from IBM 1. In IBM 1, you get only these states. So these states, these are the mixed symmetry states. They contain antisymmetric pieces, and they are new states that only appear in IBM 2. Okay? Although you have the Hamiltonian, you have equal parameters for protons and neutrons. But the space is richer.
The breaking comes from Majorana interaction.
Yeah, and the breaking, so yes, so they appear at, so this is a 1d boson state, so you have nd is 1, so you have the excitation energy epsilon, plus they are mixed symmetry, so f max minus 1, then the value of this operator is 1, so you have lambda. So they occur at energy lambda plus epsilon. This occurred at epsilon, this at lambda at epsilon. You say lambda is here 1.7 or so. Then these states are shifted to here, and this is 1 MeV higher. So new states appear that have a minus sign in that way. So we have discussed so far the U5 limit in this F spin limit of the SD IBM2. So where the F square operator commutes with F. That is restriction. And then these groups U nu 6, so neutron U6 times proton U6 reduces to a proton neutron 6 and the proton, and then you can have the U5 chain U5, O5, O3. So in that limit, you can diagonalize the Hamiltonian and you can write it as a series of Casimir operators that occur in this chain that you have discussed at length yesterday in the lecture of Professor Joly, and you obtain an analytic solution that has constants in here and quantum numbers occur, I mean 2 quantum numbers for the d bosons and 1 and 2 that are related to the F spin. And this is the Majorana operator, as you can write it here. So the message is there is an analytic solution with an energy formula in terms of these quantum numbers, and this is from the Van Isacker review, this figure. So you have this ground state, the symmetric quadruple excitation, the symmetric 2-phonon triplet, 3-phonon states, and then these are all symmetric states, and then come the mixed symmetry states. They're only a part of them, right? I mean, there will be more symmetric states depending on the number of bosons that you have, and there will be more mixed symmetry states, but they're only the lowest ones. So you have the one quadruple phonon excitation, the mixed symmetry, and then you have this full quintuplet of states, 0 plus 1 plus 2 plus 3 plus 4 plus, and they are split somehow with an L squared term. So with this term they are split up such that you can better distinguish them. And also in the other two analytic, in the dynamical symmetry limits of the interacting boson model 1, you get solutions in the interacting boson model 2 in the F-spin limit, which is the SO3 limit for the rotors and the O6 limit for the gamma soft nuclei. This I will not discuss so much here, but the rotors, I mean, you see that all these excited states, they form bands that we have discussed this morning also in the context of the confined beta soft rotor model. But there appear mixed symmetry states with the lowest band that is a K equal 1 band. A K equal 1 band does not occur in the IBM1 as the IBM1, but it occurs in the IBM2, and that has historically quite important role because this band head is a 1 plus state that was the first experimental example of a mixed symmetry state, which I will show you. Okay, so the third takeaway message is, so we have discussed the Hamiltonian for the IBM, we have discussed F-spin. The F-spin limit of the IBM2 has 3 analytic solutions. They correspond to the IBM1, so to the analytic solution of the IBM1 U5 limit, O6 limit, SO3 limit. But in contrast to the IBM1, new states appear, those with non-maximum F-spin, the mixed symmetry states. Other questions? Okay. So, how do we find them experimentally? What, I mean, we can try to measure our levels and then fit the Hamiltonian parameters to the level scheme, and then try to look for extra states and then identify them with a mixed symmetry state. But then we cannot really be sure if these were the right states. We need more. We need unique signatures for these states in order to identify them experimentally from the many, many excitations of a nucleus. The experimental signature for mixed symmetry states are magnetic dipole transitions. We haven't discussed M1 transitions before because they are not very well described in the IBM1. So the M1 transition operator is, well, maybe there's one step missing. Yeah? The magnetic dipole contains the momentum 1. So the only operator that produces angular momentum 1, which contains a boson creation and annihilation operator, is in the IBM is d dagger d coupled to 1. D dagger d coupled to 1, which is proportional to the angular momentum operator. Now you can have this for protons, then you have the angular momentum operator for protons, or you can have it for neutrons. And the M1 transition operator, do we have something else? The M1 transition operator must be constructed out of angular momentum 1 operators in the IBM1. So Tm1 is equal to the proton angular momentum operator times a G factor, an effective charge if you want, plus a neutron angular momentum operator times an effective charge. And the total angular momentum operator, L, which is a good quantum number for all states, is the sum of the proton and the neutron angular momentum operator. Since all states have a good angular momentum, it is all state, or this operator is diagonal in all states, so it cannot produce transitions. So then you can write this operator in terms of the sum and the difference. The sum is the total. That cannot make a transition, and the difference is here. So you have then the difference of proton neutron G factors in front, and some constants which we can neglect here, and you have the difference of proton and neutron angular momentum operators. how does this operator act on the mixed symmetry state? So remember, for the two bosons that we have the wave function of the mixed symmetry quadrupole phonon excitation. So we have S dagger nu d dagger pi minus S dagger pi d dagger nu. And now this operator acts on it. So this piece transforms a d boson proton into a d boson proton. So it connects this piece to that piece of the first two plus state. And here's a minus sign, and this piece transforms a neutron d boson into a neutron d boson again, but it changes the sign of this term, so it produces this plus sign here. And the total angular momentum cannot contribute to M1 transitions. So the M1 transition operator transforms the mixed symmetry state into the symmetric quadrupole phonon excitation, which means there is a strong allowed matrix element between these states. So you have large M1 transitions between the mixed symmetry state and the symmetric state. Or in other words, M1 transitions are of isovector nature, and it changes the isospin of this boson wave function, the F spin. And usually, I mean, you take the pure orbital values of the G factors. That means for protons you have 1, for neutrons they are uncharged, we have 0, nuclear magneton. So then G pi minus G nu is about 1 mu n times some constants in front which are of the order of 1. Then you expect matrix element between M1 matrix elements between mixed symmetry states F max minus 1, F spin F max minus 1, and F spin F max of the order of 1 nuclear magneton. So, and these are very large M1 matrix elements. Typically, M1 transitions between symmetric states are of the order of 10 to the minus 2, 10 to the minus 3 mu n square between the low energy states in the level scheme. And those that we have discussed this morning. Yeah, yeah.
Just one remark because the question came. In the formula you are missing Ku plus Ku. So
Here?
Yeah.
Yeah. Okay, so this unique signature for the mixed symmetry state, at least in the vibreaker limit, is there must be a 2 plus state, which is a 1 phonon state, but antisymmetric. So where protons and neutrons have opposite signs here in the wave function. There will be a strong M1 transition to the symmetric first 2 plus state with the matrix element of the order of 1 nuclear magneton. And an E2 transition, which is, at least it's a 1 phonon state, but protons and neutrons work in opposite directions, so it's a sort of reduced, so it's not so collective as here, but has some collectivity, let's say a widespread limit. And then, so this was the 1 phonon to 1 phonon transition. You can have higher phonon states, as we have discussed previously, so this is QSQM. If you have 2 bosons only, there's a 1 plus 3 plus state. Now you can transform the mixed symmetry quadrupole phonon into a symmetric quadrupole phonon. Then you end up from this 2 phonon state, you replace this by QS, you end up in the 2 phonon state. So you expect also strong M1 matrix elements from the higher multiplets to the higher multiplets here. Mixed symmetry to symmetric, right? Okay. Why is that M1 transition actually a good signature? I said before all the others are small, but why is that so? You can find the reason in the review article of Professor Isaker. You can write the M1 operator also a little bit different. Here is it. So here you see also this analytical factor, square root of 3 over 4 pi. G pi L pi plus G nu L nu in nuclear magnetons. So you can write that as the sum, L total is L pi plus L nu, but in a more fancy way, where back here you write it as L pi over N pi minus L nu over N nu. And this equality holds. I mean, you can check it. So the total the total angular momentum operator is diagonal, cannot make a transition, right? So we can forget about this piece when we discuss transitions. Now you are left with this piece here that is able to produce transitions between states. That was, so we can forget about this thing. But now let us consider only symmetric states, the IBM1 states. So not those that have a mixed symmetry character, only the symmetric ones. Then there is a relation that if you have an operator, a one boson operator, so B dagger B, so one annihilator, one creator, between symmetric states, those that have F max, independent of all the other quantum numbers, then this will be a certain constant, which depends on the other quantum numbers, times the number of bosons of this type that you have. So this is just proportional to the number of bosons that you have of this type. Which means that when you plug this operator between symmetric states, so F max states, then the L pi operator put here, that is d dagger pi d pi, produces a constant times n pi. And this L nu produces the same constant times n nu. So that means there is a constant n pi over n pi minus the same constant n nu over n nu. So the constant goes out, and then you have 1 minus 1 is 0. So also this piece back there is 0 when it comes to M1 transitions between symmetric states. So that is the proof that in the IBM1, M1 transitions are forbidden between symmetric states. On the other hand side, we said mixed symmetry states produce very large M1 transitions. So M1 transitions are a unique signature to find the mixed symmetry states. Okay, because they are forbidden between symmetric states. No M1 transitions between full symmetry states. Occurrence of sizable M1 matrix element of the order of 1 nuclear magneton, a strong signature for mixed symmetry states. So that is the takeaway message 4. M1 transitions with matrix elements of the order of 1 nuclear magneton in size are unique signatures for mixed symmetry states. Okay, there were trials before to find these mixed symmetry states by not measuring the absolute M1. That is quite difficult. But to look at E2 to M1 multiple mixing ratios, so intensities that goes by E2 divided by intensity that goes by M1, and if you have small values, then you hope that maybe that means that the M1 is large. But that is not always unique. It's better to look directly, absolutely at the absolute M1 matrix element, which is, however, difficult. I don't discuss this detail. So one way to excite these 2 plus states, the one phonon mixed symmetry state in a vibrator, is to shine with photons on them, gamma rays. You excite that level, and the cross section for exciting the level with photons is proportional to the BE2 of the ground state. If you know the branching ratio and the E2 to M1 multiple mixing ratio for the transition to the first 2 plus state, then you can get an absolute M1 matrix element out. And that was an example of Bari 136, where we did this for the first time in photon scattering. You have several 2 plus states in Bari 136, but there's one 2 plus state at 2.2 MeV, which has a large M1 matrix element. The BM1 value is 0.25, and that means the M1 matrix element is 1.1 nuclear magnetons. Because maybe we are not all aware of the fact that the B pi lambda from an initial state to a final state is 1 over 2j initial plus 1 times the square of the pi lambda matrix element. So if Bm1 is 0.2, or if the matrix element is 1 nuclear magneton, in square is still 1 nuclear magneton square, divide by 2 times 2 plus 1, so it's divided by pi. That means 0.2 un square would be the Bm1 value if the matrix element is 1 nuclear magneton. And that is what we have seen there. The same method, photon scattering, also excites 1 plus states. So with this method, one can identify both the 1 plus mixed symmetry state and the 2 plus mixed symmetry state. So the height of the peaks is proportional to the cross section from the ground state. And if you know the decay path, you can tell the M1 transition rates, and you can identify these states as mixed symmetry states. The interesting point here is there was also a gamma ray spectroscopy study of molybdenum-94, where one gets a direct transition between the mixed symmetry states, the 1 plus mixed symmetry state here to the 2 plus mixed symmetry state, in a coincidence gate on the decay of the mixed symmetry 2 plus state. That is this transition here. So that was the proof of the fact that these structures, the mixed symmetry states, they form a class of states with the same structure. So molybdenum-94 was investigated extensively with respect to these low spin states, and that is a part of the level scheme, where blue means strong M1 transition, and the blue numbers give you the M1 matrix elements. They are measured. And green means E2 transitions, collective E2 transitions between states with the same F spin. And red means E2 transitions with between states with different F spin. So you see this bottom part of this phonon structure of molybdenum-94, so it has 52 neutrons, so it's 1 neutron boson away from the n equal 50 shell closure. So it's a vibrator. With the first 2 plus state with an energy 871 keV, close to 1 MeV, and the 2 phonon states somewhat close to twice this energy, with some splitting. And then there's a third 2 plus state here, which has a strong M1 matrix element to the first 2 plus 1.7 nuclear magnetons. And there are 1 plus and 3 plus states on top that have strong M1 transitions, not to here, but to the symmetric 2 phonon states. So 2 phonon to 2 phonon. The 1 plus can decay only to the 2 plus 2 here, and the 3 plus by M1. M1 can change spin only by 1 unit of H power. So the 3 plus can decay to the 2 plus 2 and to the 4 plus 1. And also these M1 matrix elements are large, 1.2 nuclear magnetons for this transition and 0.7 nuclear magnetons for the first 4 plus. And there are transitions that I have shown you before the evidence. There are transitions from these states to the state, to this, so from the 2 phonon states here to the 1 phonon state there. That corresponds to the annihilation of a symmetric quadruple phonon. So should in principle be as collective as this one, so 16 Weisskopf units. But well, we don't have it so nicely. We only have limits. So the 3 plus mixed symmetry to the 2 plus, the 2 phonon to 1 phonon is larger than 1 Weisskopf unit and smaller than 72. So okay. At least it's consistent. It's not inconsistent to this strong collective E2, and there's a limit for the 1 plus to 2 plus mixed symmetry. It's larger than 3 and smaller than 27. Okay, now you can ask the question, are there more states that look like this? So do we confuse ourselves, or is it trivial? There are many states that have this property. No. If you want to find this out, you have to measure all 2 plus states. You have to measure all the M1 matrix elements in the decays to the first 2 plus, which means you have to measure the lifetimes, the complete decay scheme. You have to know the multipolarity of the transitions, E2 or M1. You have to measure them all. And that takes a lot of time, but can be done, but only in few cases, right, in order to demonstrate that these things are real. So therefore, I mean, this is available for molybdenum-94. So we have measured the VM1 strengths from the excited 2 plus states up to the 8 2 plus at about 3.5 MeV to the first 2 plus state, and there's only one, only the third 2 plus state, which has a large M1 transition to the first 2 plus. So this is the unique mixed symmetry 2 plus state.
And this is the B2 excitation strength from the ground state to all these 2 pluses. And this is on a log scale. So this is dominated by the symmetric 1 phonon excitation, the first 2 plus, of course. But the mixed symmetry state is also 1 phonon excitation, and it has also a large, here the second large E2 excitation strength of the order of a few Weisskopf units, 2 Weisskopf units. Okay. If you want to identify the 2 phonon states, you have to do exactly the same also for the higher spin states, or for the other spin states. So you have to measure the M1 strength distribution from all the excited states to the, let's say, to the second 2 plus state here, which is a 2 phonon state, which again is a lot of work. We have not so many data here for 1 pluses. But the first fact is you observe states that have large M1 matrix elements. So this is 0.3, 0.3, 0.3 mu n square for this going up in order to have always the same spin factor in front here. There was where is it? Here, there's a 1 over 2j plus 1. So since these final spins, they differ, I have plotted it in such a way that it always starts from the same state. So this is always the same constant here. So you find M1 transition strengths that are always 0.3 mu n squared. So they all have the same M1 matrix element. So that already indicates that they have the same structure. They all occur at 3 MeV, and there are other states that have much smaller M1 strengths to the second 2 plus state than these states here. So you can identify these states as the 2 phonon mixed symmetry states in that way. Okay, so I have discussed this already. So now we have identified the 1 plus and 3 plus states up there as 2 phonon mixed symmetry states from the M1 transition to the symmetric 2 phonon states. And you want to know if they are really connected, if they really form an entire class of states with the same F-spin quantum number. And that was this observation of this transition between the mixed symmetry states of 2 phonon and 1 phonon character. Okay, well, we discussed this already. So, takeaway message 5. Mixed symmetry states have been identified to form an entire class of states from the measurement of absolute M1 transitions. And the best known example for the vibrational mixed symmetry states is given by the level scheme of molybdenum 94. Now, I've discussed already photon scattering, an experimental method that was used recently strongly to investigate these mixed symmetries. The 1 phonon mixed symmetry states was Coulomb excitation. And therefore, I want to show this method, how this works to you, and how one can identify the mixed symmetry states there in these reactions. So Coulomb excitation means you excite a nucleus by another ion that passes this nucleus, but they wouldn't touch. They do not interact by the strong force. They just interact by the Coulomb force, because there is a fast passing charge that produces exchange of virtual photons. So you can excite the nucleus when it absorbs them, and it will excite predominantly 2 plus states. We want to look for 2 plus states. And the E2 excitation strength is proportional to the cross-section that you can measure. So you can measure how often you have excited that nucleus to that particular state, and you have the cross-section, and then you know the E2 excitation strength, which means when you know the decay pattern, you know its lifetime. Traditionally, you do this with light ions on a heavy target when you want to investigate a heavy nucleus, but if you don't, you can also do projectile Coulomb excitation. So you turn this around, you shoot with a heavy nucleus that you want to investigate on a light target, and you excite the heavy nucleus. Then this is called projectile Coulomb excitation, because a projectile is the nucleus of interest. And then you can look at the gamma rays that come out of this nucleus with a large detector array for gamma rays, and you can measure gamma ray angular distributions and gamma intensities, of course. So from the gamma ray angular distributions, you get the multipolarities. You need to know them because you want to extract also E2 to M1 multiple mixing ratios, because you want to measure finally an M1 transition strain. And you can measure spin quantum numbers, so you can make sure that you see 2 plus states, or that you can distinguish the 2 plus states from 3 minus states or 4 plus states. And from the gamma intensity, you get the gamma decay branching ratios out. You get out how often the level was populated. The more it was populated, the higher is your intensity for the decay that you observe. That means you get then from the total population, from the total reaction yield, you get the excitation cross-section, and from the excitation cross-section with all this information, you get then the absolute lifetimes and the absolute transition rates. So everything what you need.
Excuse me.
Yeah?
Just a question. You described that you have two ways of doing it, either direct kinematic or inverse kinematic.
Yes.
Maybe I missed it, but what is the interest of the inverse kinematic? Because of course you will have to take into account the Doppler effect. That's going to be
Right.
So
Yes.
would it be like for
This is much more complicated than this one. So people have mostly used this technique, and also the resolution is better, so it sounds like really stupid doing it this way. Now the funny thing is, so when you shoot a light, here I have the example of cerium 138. Let's suppose you want to populate low spin states, so you want to have a light particle and a large particle, because you don't want to have too much multi-Coulomb excitation. So if you shoot, let's say, carbon on a heavy nucleus like cerium, close to the Coulomb barrier, you are for sure above the Coulomb barrier for carbon on oxygen, carbon on iron, carbon on aluminum. So that means that you are above the Coulomb barrier for every material that is in your experiment. I mean, your target chamber is made out of aluminum or out of steel, so you scatter particles and you produce reactions there. So that means you have a lot of background, and that does not allow you to measure the Coulomb excitation in gamma ray singles. Or in singles, you are only sensitive to the IRAS bands. You see them very strongly, but you need singles because you have to identify the transition to the ground state in order to observe the 1-phonon states. If you do it inverse, and you must make sure that you are with a heavy particle below the Coulomb barrier on carbon, then you are for sure below the Coulomb barrier to everything else in the experimental setup, because there is no boron, lithium, and so in your setup, and beryllium. So that produces very, very clean spectra. Or you can use gamma ray singles, which you anyways have to take in order to measure the transitions to the ground state. And the gamma ray singles allow you to use an enormous count rate, such that you see also very weak population bunches. And this was actually the trick of this approach. So you come with your heavy nucleus, scatter it on carbon, you Coulomb excite it. It will de-excite, so you hope that you have excited it to its 2 plus fixity state. It will either de-excite by an E2 transition to the ground state, or it de-excites by the M1 transition to the first to plus, which you have to measure. I mean, the E2 to M1 multiple mixing ratio and the decay transition rate. And then that decays to the ground state also, and you measure these gamma rays by your detector array. And here comes the point. So we did this you need a big accelerator. So you are talking about half a GeV of energy for these ions to come close to the Coulomb barrier. So you see cerium 138 at 480 MeV. That was done at Argonne National Laboratory near Chicago. This is singles in this gamma sphere detector array. And here you see the count rates. That is the first 2 plus state. Here's a log scale. The first 2 plus state, there are several channels wide, and the count rate here is several millions per channel. So you have an enormous count rate. That means you have an enormous sensitivity. And what we are interested in is these structures here. So that is at least still like a couple of thousand counts per channel. This one is the E2 decay to the ground state of the 2 plus mixed symmetry state, and that is the M1 transition here, this one here in the middle, the M1 transition to the first 2 plus state. And this is only possible because we can count so fast and we can use gamma ray singles. And this is possible because we are inverse and we have no nuclear reactions. And this is now also applicable to exotic nuclei, because exotic nuclei, in radioactive beams, you can use them in order to do this projectile Coulomb excitation, but you cannot make a target out of it. So you can do these at this radioactive beam facility. So that was done in argon with the Atlas superconducting LINAC, so heavy ions with 80% of the Coulomb barrier using the gamma sphere detector array, 100 germanium detectors shielded with, from Compton scattering events with anti-Compton shields, and we have done a series of experiments in order to extract the M1 transition strengths. Now I show you how this works. So in this case, we observed all 2 plus states up to 2.7 MeV. So we expect this 2 plus mixed symmetry state to be located at around 2 MeV. But we have to measure them all. We have to identify them all. And measure the M1 transition strength to the first 2 plus states. So that is the single spectra. But of course, you also have coincidences with these big detector arrays. And that one is the 2 plus mixed symmetry state, which I will show you now. So first, you have to identify spin quantum numbers and E2 to M1 multiple mixing ratios. So you do this by angular distributions. So the angular distribution function, so you have an initial state J, I, a final state J, F, an E2 to M1 multiple mixing ratio, and the observation angle theta. And then you can, angular momentum theory, you can decompose this into orientation coefficient, into some parameters that depend on this on the spin quantum numbers and the multipolarity of the transition and the Legendre polynomials. So let's consider the mixed symmetry state. So that is the 2 plus state at 2.237 MeV. So from the ground state transition, we observe an angular distribution from which we obtain these asymmetry parameters A2 and A4 that occurred previously in this formula for the multiple for the angular distribution, and we can tell that this is a quadrupole transition. From this distribution, angular distribution, we get the A2 and A4 coefficients, which gives us the alignment of the states. So that is the probability for the M substate population. It's a 2 plus states, so it has M substates from -2 to +2. They lie on such a Gaussian. So here you see the data points. Now we know the M substate distribution, and we observe also the transition from that state to the first 2 plus state, of which we want to measure the E2 to M1 multiple mixing ratio. But now we know already the M substate distribution, so this we can plug into an expected angular distribution coefficient plot as a function of A2 and A4, these are symmetry parameters. For this M substate distribution must be this curve as a function of the E2 to M1 multiple mixing ratio. So here is pure M1, here is pure E2, and in between that is mixed, and that is what we measure. Yeah, so this is the best value is a very small E2 to M1 multiple mixing ratio, 0.1 something here, it's 0.18. So that means that is 97% M1 transition strength. So first we have measured now the E2 to M1 multiple mixing ratio and the spin quantum number. Then from the gamma ray intensities, we get the population cross sections, we get the yields. So we normalize everything to the first 2 plus state, which has a known lifetime. So the first 2 plus state is 1. The second 2 plus is populated at a level of 1%. This 2 plus state here, that is of interesting, is populated to a level of a few per mil. and there are other 2 plus states for which we can do this sort of analysis. Now we know that the Be2 excitation strength of that state, and we can do a Coulomb calculation with a code for this multiple Coulomb problem, and then we get the B sigma lambdas for all the transitions out. And from the branching ratios, we have the lifetimes. And that results in these lifetimes. So we have the first 2 plus state, second, third, fourth, fifth, sixth. We have all these lifetimes, and we get the E2 to M1 multiple mixing ratios out from regular distributions, and then we get the M1 transition rates. This is for a neighboring nucleus cerium 134. That is a plot of the same experiment. And here, a distribution of M1 strengths to the first 2 plus as a function of energy from 500 to 2.5. And there's one state here which sticks out, which has a large M1 transition rate of 0.3 mu n squared. So this is the 2 plus mixed symmetry state in that nucleus. The same happened in cerium 138. So we have done this at Atlas on a couple of stable nuclei in the mass range about 130, so xenon, barium, cerium, samarium nuclei. And that came out of this series of experiments. So a distribution of M1 transitions from excited 2 plus states to the first 2 plus states. And here that is n equal 80, so n equal 82 would be next. At n equal 82, you have a neutron shell closure, so no neutron bosons, which means no mixed symmetry states. Right? So therefore, n equal 82 is not shown. It starts from n equal 80, n equal 78, 76, 74, and so on. So if you have, so close to the shell closure, you have good vibrators. You always find this one strong and one transition. Here it is fragmented into 2. There is a discussion why it is so. Most likely that is related to the fact that at cerium, 58 protons, you are at a situation where the G7 half above Z equal 50 is closed, and that produces a fragmentation. So you cannot, in the valence shell for protons, you have 8 protons in the G7 half, it's full, and then you cannot make a D. So you have to lift the particles to a higher excitation, and that produces then this fragmentation. At least there's some M1 strength there, but here is very well developed symmetry state. And then when you go towards mid-shell, you start to deform the nuclei. So here is a sort of the phase transition to deformation. This M1 strength decreases, and we cannot find it anymore here, which was unexpected, though. We expected that it would stay everywhere. I mean, this is still under debate. Maybe it shifts to higher energy and it escapes our observation. I mean, that could be, yeah?
When you say you couldn't find it, it means it's a lower limit, right? Yeah, I mean, you have error about the fact that you do not find.
Oh, yes. First of all, well, it could be more fragmented that all the fragments have M1 strength that is below our detection limit, which, however, would mean that this state has dissolved. I mean, it disappeared. Or I said we were sensitive to all 2 plus states up to 2.5 or 2.7 MeV. Now, if that state is shifted to higher energy, we are not sensitive to it anymore. Right? So maybe both, it fragments and shifts to higher energy, as it should actually, then it would escape our detection, and therefore this is spot is empty.
But look at the energy is not changing, just the cross section is changing. If it's shifting to high energy, do you think it would shift like immediately? Because the energy of the M1s.
2 MeV, here's already 2.2. Yeah.
Yeah, but it stays about from a little bit below 2 and a little bit above 2. So you have a sudden drop of the cross section.
But in these deformed nuclei, the experiment is more difficult because the first 2 plus is lower lying. It sucks much more cross section, so we count much more. We have a limit on the count rate that we can afford in the experiment. So we have to reduce the intensity, so we are less sensitive. So in these nuclei, we are sensitive to 2 plus states only up to 2.2 MeV. For that reason. And 2.2 is exactly the energy where it is already here. So, I mean, that it's not unlikely that we have this one.
Could it not be that the 1 plus comes below the 2 plus?
Not here yet.
Not yet.
Because they are not SU3, they are more like between, the xenons are between U5 and O6. So you have a sort of O5 pattern, and then there's a 2 plus tau equal 1, and the tau 1, tau 2, 1, 1 states above them.
Because as far as I know, but maybe you know better, on top of the 1 plus in the fourth nuclei, never the 2 plus has been observed.
Oh yeah, but there is a transition. This hasn't been has never been observed, that's correct, apart from a person who is in this room, which is Herbeck. Maybe he has first indication of the 2 plus state in the scissors band. And Achim Richter claims that in 84 he has seen it, but this is wrong. Because no, we can prove that this is wrong, because Herbeck has the data.
Did you ever try a semi-magic nucleus to see that you don't see anything in M1 state?
Yes, we have a beautiful data set on xenon 136 because we wanted to do alpha transfer on carbon to radioactive barium 140 in order to see this mixed symmetry state there. There was a theory with Vituri, but it didn't work. But we have a very nice data set on xenon 136. First 10 2 pluses or so with all the lifetimes. It's not yet finished. I mean, my student Christian Stahl is working on that. That will come soon. So, and I don't think there's strong M1 up to 3 MeV or so. Okay. Then you have seen here in this corner there's something missing. I mean, you have this evolution of this M1 strings. Stable nucleus, xenon 134 is stable, and then there's tellurium 132, which is neutron-rich unstable. And I said we can do this technique also with radioactive beams. So this was done at Oak Ridge. Miroslav Danchev has taken data for some different reasons. And there is a 2 plus state at some energy here. I forgot that you have to add these values. And then there is an expected 691 keV transition, which would be the strong M1. And this state was seen in Coulomb excitation. Unfortunately, the branching ratio is not very well known. It has a very large error bar, which means that we get the VM1 value only as a lower limit, but it's larger than 0.2 mu n squared. So it's clear that this is a mixed symmetry state. So that now makes this systematics a little bit nicer. So I mean, this is shifting to lower values. So the mixed symmetry state is here already at 1.6 MeV in tellurium 132. So this is the first application of this method for the mixed symmetry states to radioactive nuclei. And you see now this splitting from the proton-neutron interaction. What you see here is the energies of the first 2 plus states as a function of proton numbers in the n equal 80 isotopes. So this is tin 130, tellurium 132, xenon 134, barium 136, cerium 138. And so the first 2 plus states are known here. So they decrease. The larger you make the valence space, the more collective become the first 2 plus states, and it goes lower in energy. And here you see the mixed symmetry states from tellurium, radioactive, and then xenon 134. And so you see this splitting. The larger you make the valence space, the larger becomes the proton-neutron interaction, the more does the symmetric and the antisymmetric state split. So you can measure locally the proton-neutron interaction in the valence shell. Okay. Takeaway message 5, Coulomb excitation is a great method to study the 2 plus 1 mixed symmetry state. So the one phonon mixed symmetry state, at least in vibrational nuclei. There was a question with the 1 plus, the 2 plus on top of the 1 plus. We have also tried to do this when we go to deformed. So we did samarium 154, but that was too difficult because the first 2 plus states were already so low, has a very large intensity, and we weren't sensitive. That's very difficult. Okay, now in the last 2 minutes, I want to convince you on the fact that this antisymmetry actually can be measured directly. That is the defining characteristics of this mixed symmetry state, that there's a minus sign here between proton and neutron parts. If there are more than 2 bosons, it is only one piece of the wave function, but there are some antisymmetric pieces. But this seems to be impossible to measure, but there are some evidences that prove this or that support this antisymmetry. So if you want to be sensitive to proton pieces and to neutron pieces independently, what can you do? You can study the protons by charge, by Coulomb excitation, or by electron scattering. Electrons are only sensitive to the protons. And you can study the mass by hadronic reaction, so do proton scattering. So let's compare electron scattering and proton scattering. And let's do it on molybdenum 94 or zirconium 92, which is very close. So you need an electron accelerator if you want to do the electron scattering experiment. We have it in-house. We have this superconducting Darmstadt linear accelerator, which is a 130 MeV machine. In principle, we can do 70 MeV, 100 MeV electron beams. Oh, there's a photograph. I skipped this. We have done electron scattering on molybdenum 94, where we know exactly where the mixed symmetry states are. And surprisingly enough, that's a very large signal. So this is the elastic line, that's the ground state, electron scattering on the ground state, electron scattering on the first 2 plus at 70 MeV, first 3 minus, and this one is the third 2 plus, the mixed symmetry state. It's very large. Well, of course it's large because it's a one-phonon state. Electron scattering populates predominantly one-phonon states, right? Because electrons are relativistic. They just exchange one virtual photon in your excited state, and then you have the one-phonon state. And we see many other 2 plus states, up to the 11th 2 plus states. And then we compare this electron scattering to proton scattering. Also proton scattering, that was done at 200 MeV, produces sort of the same spectrum, same resolution though, 30 keV about, first 2 plus, mixed symmetry 2 plus, first 3 minus, and then many other 2 plus states. And now, my time is up, but so here you see that is now same data on zirconium 92. We also know what the mixed symmetry state is. The point is, here you see the diffraction pattern, cross-section proton scattering, cross-section electron scattering as a function of momentum transfer. And you see in proton scattering, you see this shift in transition radii, systematically. The transition radii shift to smaller momentum transfers for the full symmetry state than the mixed symmetry state. So the mixed symmetry state has a smaller transition radius, because then the diffraction pattern are expanded. And in the electron scattering data that are sensitive to the protons, you see that this is independent of the momentum transfer, which means they have the same, I mean both states, that is now the ratio, they have the same transition radius for the charge, the same proton transition radius. So from these experiments we know that the matter transition radius for the 2 plus mixed symmetry state is smaller than the matter transition radius for the first 2 plus state. But we know that the charge transition radius, they are equal. And we also know that the valence neutrons, they are sitting in the 2d5 half orbitals with a node, have a larger radius than the valence protons in the 1g9 half without a node. And that means then that the neutron component flips its phase. And if I would have had time, I would have made the argument, but I want to show you just the composition. So the 2 plus states of neutron excitation and proton excitation in the valence shell, they split up by the proton-neutron interaction into a collective piece, which you can obtain from the coupling of resonances, and the valence shell excitation, where the neutron component changes its phase in this situation And that was the one where the neutrons have a larger radius in the valence shell because they are sitting in the 2d5 orbital. And now you can plot the contributions to these wave functions to the transition radius or to the density of the levels. So the collective piece is equal for the symmetric 2+ state and the mixed symmetry 2+ state. The neutron piece adds to this in the symmetric state. So here it has a node 2d5, so it has a contribution at larger radii. But in the mixed symmetry state, there's a minus sign, so you subtract contribution at larger radii for neutrons. And that means you change the average location. So this is when you sum the collective piece and the neutron piece for the symmetric state, you end up here on average. And when you sum these contributions up with the opposite sign, you end up at smaller transition radius for the mixed symmetry state. That means the different neutron transition radii are the consequence of the mixed symmetry character of the minus sign. So these patterns, that is experimentally observed, also systematically, in molybdenum 94, zirconium 92, you see a systematic decrease of the transition radii for the mixed symmetry state for these cases where the neutron valence shell component has a larger radius because it has a node. And that means in these cases, the quantum mechanical phases have been accessible. Okay, I'm at the end for this lecture, and I thank you very much, and you can ask questions. Or we go for lunch.
Are there no questions?
So can we extract some neutron-proton interaction comparing electron scattering data and proton scattering data? I couldn't understand. So
No. I didn't want to extract a proton-neutron interaction from comparing these things. I wanted to obtain evidence for this funny minus sign between the protons and neutrons.
Okay.
So I want to be sensitive to the relative contributions of protons and neutrons in the wave function. But there is no probe that allows me to directly test only the neutrons. But there's a probe to directly test the protons, and there's a probe to test the sum of those. So I compare momentum transfer to the symmetric state and the mixed symmetry state for proton scattering and for electron scattering. The electron scattering have the same relative cross sections for both states, as a function of momentum transfer. It's always the same. That tells me that both states have the same transition radii. Otherwise, that function, so the ratio of these points gives this plot here. And this is constant as a function of momentum transfer. If they would have had different charge transition radii, that would have been sloped, would have been upsloping or downsloping. But it's constant. That tells us that the charge transition radii are identical for both states, for the mixed symmetry state and the symmetric state. But for proton scattering, we observe a difference in transition radii. That tells us that the meta transition, and in that way, that this diffraction pattern for the mixed symmetry state is shifted outwards. Now think about diffraction of light on a small object. So you have a larger spread when the object is smaller. So that means the meta transition radii of the 2+ mixed symmetry state is smaller than the meta transition radii of the first 2+, of the symmetric state. Both put together with the fact that the valence particles here, the neutrons, are living at a larger radius on average than the protons because they have a node and they don't, that together gives us this minus sign of the neutron wave function in the 2+ mixed symmetry state, while it's plus in the other. Yeah?
The GDI means applying the equitable rhythm.
Yes, well, that is just, so I was out of time, and we have compared this to a quasi-particle phonon model calculation, where you have a lot of background states that have a lot of E2 strength at excitation energies of 15 MeV or so. And all which is E2 strength, which is not in the valence contributions, is called giant quadrupole resonance. So when we do this, so we calculate in this quasi-particle phonon model, we calculate the BE2 and BM1 values as a function of the two quasi-particle energies that enter the basis states of this model. So when you use all the two quasi-particle configurations up to 50 MeV, you are converged, you have the full matrix elements. And now you can look what two quasi-particle excitations contribute to your transition rates. Then you observe the BM1 is basically made by the contributions that are in the valence shell. And when you look what contributions they are, that is neutron D5 half and proton G1 half, proton G9 half. So, and then higher lying two quasi-particle excitations do not contribute to this M1 matrix element. So it's a valence shell M1. It's just neutron D5 half, proton G9 halves, and they couple to 2 plus, and they flip their phase, and that makes the M1. It's a mixed symmetry state. So it's the neutron D boson and the proton D boson, and they contribute to this M1. While the BE2 is produced by some valence contributions from neutron D5 halves, proton G9 halves, but the majority of the E2 strength is obtained from two quasi-particle energies that have, before doing the full mixing calculation, this QPM, that have high excitation energy. And that means that is the collective, that is a GQR. Or in terms of the shell model, that means that produces the effective charges. If you would do a shell model where you have the valence shell only, you always get way too small E2 transition strengths. So you need effective charges. And the effective charges come in this model, which does not need effective charges because it has a very, very large basis, although it has some other problems. Then you see where this comes from. That comes from the 2h bar omega contributions that make the collectivity. And everything which is in here, that is called giant quadrupole resonance. So you see you need 3 contributions in order to understand the mixed symmetry state there. You need the collective component, and you need the proton and neutron valence shell components. And that is the 3-state model that we have done here. So you have the neutron valence shell component, the proton valence shell component that makes the M1s, and you have the quadrupole resonance that makes the E2.
We better stop.
Yes.
Okay.
At 1:45 we have to take